Morning, Gokul.
Morning, sir.
Dipanvita, I sent you a mail this morning also.
Hello. Yes, sir. I've seen that. I'm working on that proof as of now.
Okay. So now that's it. I mean, I've told how to choose Y0, how to choose Y1.
Yes,
You
sir.
have to
I'm just
justify,
working.
you can choose Y0 like that. You have to justify, you can choose Y1 like that. And then go on.
Yes, sir.
So, Sarbana Bishwas, where are you from? What are you doing these days?
Sir, I am from IISER, Bhopal.
Oh, you are the same person. Oh, you were introducing me. Acha, acha, you are, sir.
Yes,
And
sir.
Pavitra Nedungadi. Uh, uh, she has not yet connected. Is not yet connected.
I think participants are yet to join. You only have 5
Yeah,
people.
yeah, yeah. It's quite a bit of time. Yeah. Yeah, it's quite a bit of time. That is why I was chatting. So, Gokul, what are you doing there?
I'm a student, sir. In IISER 5th year, BSMS Mathematics.
Fifth year BSMS Mathematics. So, is there some special papers you are taking? I mean, already some.
No, sir. I currently have only my thesis work.
Huh?
Only my thesis work is left, sir. Courses are over.
What work? Thesis work. Oh, you have to write
Master's
a
thesis.
master's thesis. So, have you chosen a topic?
Yes, sir. I'm working in combinatorial optimization.
Combinatorial optimization.
I'm working under Kashyap, sir.
Good. So, are many from IISER Bhopal attending the lecture?
Yes, sir. I guess 10 to 20 are there at least.
Mhm.
I saw
Regularly?
not regularly, sir, but at least in the name list there many are there.
Huh?
In the name list many are there, sir. Regularly, I guess at least 5, 6 are attending, as far as I know.
So this is quite a different topic.
We don't have courses like this in our curriculum also related to logic.
Set theory also.
Yes, sir.
Set theory you don't have.
No, sir. No course related to set theorem as such.
Rupkatha Chand, what are you? You told me you are from Bolpur, but some college or something you named, not this, right?
Sir, it was my school. I mean, the school which I passed out from in, I mean, it is the higher secondary. It was Navnalanda Shantiniketan.
And
Yeah.
now?
Right now, I'm in IISER Mohali.
You are at IISER Mohali. What are you? I mean, at what level you are?
Sir, second year BSMS.
Second year BSMX. Are you following the lectures?
A bit, huh? Right now, a bit.
Okay. I mean, I know many persons there. I even know Kapil and Judge, what is it? Judge Professor Parsi come?
I have seen once. I have
You
seen
have
her
seen.
once. Oh no, wait. No, I've not seen him. Interesting Pasi. I've not seen him, but I've seen his office.
You have seen his office, okay. So, Vatsala, where are you from? Vatsala? Ah, okay. Good, good. And Ujjwal, where are you from?
I'm from CMI.
Oh,
CMI.
I think you told me, right?
Yes.
Yeah, you told. So in CMI, it's still BSc is common, or there's a BSc in mathematics, BSc in computer science. Is there something like that now? Something like that I was hearing.
Sir, in the first semester, we in CMI we have BSc Maths, honors in computer science, and honors in physics separately. But in the first semester, the degree is common.
In the first semester, degree is common. Only first semester.
Yes, sir.
That makes sense. That makes sense. Okay. And are there physics faculty? I know many computer science faculty. I know, of course, many mathematics faculty. Are
Yes,
there
physics.
are there
Physics.
physics
We have a
faculty?
physics department.
Oh, acha. That must be a new addition. Do you follow logic also, Ujjwal? What did you say? You are at BSc what level?
Sir, BSc second year.
BSc,
Like
and what
fourth
honors
semester.
you have taken?
Physics.
Oh, physics. Then are you able to follow the lectures, or?
Yes, sir. Like the logic part of it and the mathematical part of it, I'm able to follow. I'm not familiar with concepts like Turing machines and
Turing machine, I was just in passing mentioning, but recursive functions?
yes, sir. What I got from the lecture, I could understand properly.
Pavitra is still having problem connecting to audio for quite some time. I don't know. Ramakrishnan has attended all the lectures, I remember. Dhruva also this time could attend all the lectures. So Ramakrishnan, where are you from?
Good morning, sir.
Good morning. Where are you from?
I'm from Tamil Nadu.
No, but what are you studying?
Okay. Okay, so no, I'm a guest lecturer at SP College, Pune. Yeah.
What do you teach? Mathematics?
Yes. So I teach in the MSc program. So yeah, I was doing my PhD at IISc Bangalore, which I discontinued due to certain personal reasons.
IISc or IISc Bangalore?
Yeah.
Oh, that yeah, and you had to leave that.
Yeah, there were some personal reasons which forced me to discontinue it.
Oh, sorry.
Upon which I've taken this guest lecturer teaching thing at this SP College, Pune.
Mm-hmm. So you where you doing research in mathematics in IISc?
Math, information theory, classical information theory.
No, were you in mathematics department or computer science department?
I was in the ECE department, electrical communication engineering.
Oh, achha. Good morning, Ranjan Babu.
Yes, good morning.
Were you there yesterday?
Yes, but I came a
Good.
little late, but I was there and I could follow. And the thing that I was waiting for, I could get it. I wanted some things to be cleared, some doubts to be cleared, and I got them all cleared. Thank you so much.
Then I can ask you questions today.
Hey, my God, please don't do that. I fail. Miserably fail.
Why? You have followed. So why
I have
will you fail?
Okay, I revise my statement. I believe I have followed.
Do you come here? I know. Do you recognize her?
Yes, of course.
Huh?
We were there in Tejpur. Didi was with us. Sure.
So in Tejpur, I was giving lecture, and one photographer was very keen on taking picture, going all around the hall.
Yes. Yes.
That is what you must be missing for
today.
No, online lectures. I cannot
yes.
And
that's right. And also after the lectures that we could meet and chat and etc. These are all missing.
Yes, these are all missing. But anyway, thank God at least you are not able to point out to people and say, oh, look away, this guy is crazy about mathematics. Is he the one?
Oh.
But he was saying it on my face, so not to worry. गाना के पूरी चल वो भूलेगा चलेगा ना
একটু মনে পড়েছে তারপরে সব
আমার বইটা কিনে ফেলো এবার
কিনবো কেন আমি ডাউনলোড করে নেবো এখন পাওয়া যাবে
এই তো এত পরিশ্রম করে you know I did work so hard and now everybody is downloading and I am getting no royalty. It's coming to be near the time.
So everyone, welcome to the final day of ISLA 2020. I'll hand over the session to SMS sir. Sir, please.
Okay. So today we can be relaxed. We have enough time at hand. And first, maybe some more people will join. So first, I would like to invite questions, even from YouTube. I know there are people attending on YouTube and they transfer questions, so feel free. But here I can immediately see people if you have, because I have completed first incompleteness theorem. So only if there are no questions, I will go ahead. Yeah, I'm giving you maybe 2 more. It's only 10 o'clock. I'm giving you 2 minutes for this. Pavitra, could you join? I mean, still it is showing connecting to audio. Probably she or he is having a problem. So the way Gayatri is spelled, I'm sure she is from South India. Am I correct? Gayatri, because you have written TH. TH Gayatri. Sujata, IISER students could join?
I don't know. Maybe they joined from the YouTube.
Oh, okay. Okay. Yeah, YouTube also many are listening. I am aware of that. Huh?
So
okay.
Gayatri has responded in the chat that she is from the south.
Yeah. Because you see, I was only showing off that, I can understand. So, sure. Because the spelling TH gave in that. Huh? Okay. So, let me share a screen. And wait, this is not what I want to open. I want to open some other thing. This is what I want to open. It was covered under it. Huh? So, I think, is the size okay? I mean, no need to maximize. Is there a need to maximize it?
No, sir, it's readable, sir.
Readable is fine. So, this is where I left you. Now, sorry, yeah. Okay, so let me go back a bit. Yes. So here, for example, if I literally say that T is an extension of N, then, you have to begin with those concepts and such. And it is not all theory does that. So there is this notion, interpretation in an extension by definition. And I only, it takes time. These are just a lot of definitions and some minor theorems. But you have seen an example, already you have seen that in set theory, you can introduce the symbol empty set. Okay, and that has a definition. So extension by definition. Okay, so once you have proved the existence of and uniqueness of empty set, and you know what is the formula to define this, it is X is empty if and only for all Y does not belong to X. So that is the definition of empty set. And there's a unique set, so you can introduce a symbol, which we generally do by phi, and add an axiom Y belongs to phi if, X belongs to phi if and only if for all Y does not belong to X. Okay, so that right-hand side has become the definition. Okay, and then successor. So as I told you that you can prove using axioms of set theory that given any set X, there is a unique set whose elements are elements of X and X itself, X union singleton X. Okay? I mean, this is usual, like union of two sets is sets, and this if X is a set, then singleton X is a set. These are just followed from axiom. So you have to put the axiom to prove it. And now you can show Sx. What is the definition? Y belongs to Xx if and only if Y belongs to X or Y is equal to X. Okay? And therefore now you can, and that this set is unique, is also easily proved. So now you can introduce a unary function symbol. So that is called extension by definition. Okay? So this is called extensions by definition. And the theory does not change because you are actually doing the same ZF. Okay? So what is it called is a conservative extension. That whatever you can prove in this extended theory by replacing each symbol, new symbol by its definition, you get back to a formula of original theory, and that is a theorem in the original theory if and only if this is the theorem. So you are actually not changing the theory. So that is the meaning of extension by definitions, and then interpretation. So like here, let me tell you, this interpretation will always also involve universe, as if there is a model of your theory N inside ZF. So there is an axiom called axiom of infinity, which will prove that collection of all natural numbers is a set. Okay? And actually this particular set is what is called a standard model of number theory. Okay? So inside ZF, now you have got hold of a sort of model, and then you restrict all your zero is there. So interpretation empty set is the interpretation of zero. Then belongs to is the interpretation of less than. Then X union X is the interpretation of the capital X function, and so on. And now this whole thing means that in this model, whatever formula you take of is this extended language, but you think that your universe is now omega 0 only, the set of natural numbers only. So whenever you say for all x, you say for all x belonging to omega 0. Whenever you say there exists x, you say there exists x belongs to omega 0 and blah, blah, blah. Okay, this is called relativizing any formula to omega 0. Okay, and this will mean that I have an extension by definition of T and a set, non-empty set in, that is introduced by a unary function symbol, whose definition would be that x belongs to that unary function symbol if and only if x is an integer. X belongs. So there is this, and you are relativizing all that, and your theory T should be able to prove all the axioms of N relativized to that omega 0. Okay, and indeed, axioms of set theory proves usual notion of usual axioms of number theory. In fact, that becomes a model of piano axioms. Okay, and that is what is called a standard model. So I have given you as well as possible, given the time, this notion that a theory has an interpretation in another theory by an has an interpretation in an extension by definition of a theory T. Okay, and this is what people informally say that if your theory is as strong as, at least as strong as N or stronger than N. Okay, and if that is axiomatized, then that is incomplete. Okay, this is not very hard from what I have to prove from what I have proved. Huh? But these are just minor details, and the time is not sufficient to do this. Okay, so and as I told you, that remarkable thing about Gödel is that he gave a definition of recursive function in such a way that the fraction of number theory that he uses is rather small. Okay? With other definitions, also one can prove this. It's very clear one can prove if it can be done here. But then this theory has to be stronger. Okay? And many books avoid it. I don't know why. Because, well, I can guess that the reason is that they don't want to go through the ordeal of beta function. Okay, so this is first incompleteness theorem. And then later on, yesterday night, I was thinking that, oh, students must be thinking that if there is a first incompleteness theorem, at least there must be a second incompleteness. Okay, indeed there is. Okay, and some of you may have heard the slogan that mathematics can't prove its own consistency. That is what Gödel proved. But you see, all these are like the first incompleteness theorem. It is a completely precisely stated mathematical theorem, and it is totally a part of mathematics. Okay, it has been applied to a question in logic, which actually usual mathematicians like Hilbert and such asked. So it is a very, very precise theorem, and I don't, at times I get very angry when I see in the newspapers and such that they are romanticizing it and not giving the correct picture. The person who is writing about it, probably most writing, in mathematics, Gödel's incompleteness theorem has been written a most outside mathematics, has been talked of a most outside. Okay, and most often, a correct picture is not given. I mean, an incorrect picture. So that is very bad. Okay, so I will say a few words about what is second incomplete. It is possible now for me to state second incompleteness theorem, and proof is, of course, again, quite long drawn, and this time it is very intricate also. So proof I'm not presenting. I'm only stating the theorem, and then I will tell you that roughly I will explain what does the slogan mathematics can't prove its own, which you may have heard. Okay, so this part will only state the second incompleteness theorem. So now I am taking a finite means only finitely many non-logical symbols have been used, axiomatized theory such that I have made a mistake. Actually, now it is in for the second incompleteness theorem, it is not N. It is piano arithmetic. I should have written it PA. So piano axioms is the usual axioms of number theory that is taught to you. There is the way it is taught. One of the axioms, the most crucial axiom, is that every non-empty set of natural numbers has a least element. Okay. Now, how do you convert it? I mean, how do you convert it into a formula? Now, one of the things you have already been told that this is not a first order sentence first. Okay, it is a higher order statement because there is a quantifier over subsets. And you want to use it by a formula or by a set of formulas. Okay. And you know if the theory is finite, then there can be at most countably many formulas. Okay. So you don't have to assume piano axiom in that generality that for every non-empty subset, that means for all non-empty subset, there exists a least element in that. Only countably many will do. So what people do is that take a first order formula of number theory, the same language, with one free variable x, and then you make the statement that if there exists x, phi x, that means the set of all x such that phi x holds over natural numbers, I mean, if that is non-empty, so that is why I said if there exists x, phi x holds, that implies there exists y, phi y holds, and for all z, phi z less than y implies negation phi. That means that element is the least element. Such sets are called definable sets, set of all x, phi. So you state piano axiom only for definable subsets of this. So this is a very, very big mistake I have made. This should be piano arithmetic for the second incomplete. I will correct it. So now, in any case, yes.
Sir, can you repeat the definition of definable subset?
Yes. So you have the set of natural numbers, usual standard that we have described, and you have a formula of number theory, that means using that language number theory, with one free variable x. Okay. And there may be y1, y2, yn, but there you are allowed to plug in natural numbers, what are called parameters. Okay. So there, let me put it this way, that a subset A of natural numbers is definable if there exists a formula phi x y0 yn minus 1, and there exist integers m0 mn minus 1, such that that set is precisely those integers x which satisfies the formula phi x m0 mn minus 1. Okay?
Yes, sir. Yes, sir. So, yeah.
So that means membership to that set is expressible by a formula. Okay? It's not an arbitrary set.
So there will be only countably many definable sets.
There will be only countably many definable sets. Yes.
Yes.
Okay, there will be only countable many definable sets. Now, and you are only allowed to use the formula of ZS. Okay. So there is a, so actually in mathematics, unless you are using axiom of choice and such, you only encounter definable set. You say that, you define the set, that criterion for the membership to that set is described by a formula. Okay? Is expressible by a formula. Okay? For example, Bibi Rao has given you a hint what is a class. A class is nothing but a formula with one free variable at least x. And you think of it as collection of all those x such that phi x is true. Phi x is provable. Okay? And in mathematics, everything, collection of all topologies, collection of all groups, collection of all torsion-free abelian groups, collection of all rings. So you have when you write down the axioms and such, actually what you are writing down is a formula that defines everything. Okay? So those objects are always classes. And that is one of the saving thing for mathematics, because in mathematics you encounter sets or classes. Okay? So in algebraic topology or some other subject, you may say, oh, I'm looking at how does a category define? A category consists of a class of objects, and elements of that are called class of objects. Elements mean those x which satisfies the formula. Together with something. Okay? So whatever collection in whichever branch of mathematics people are looking, they are all classes because they all have a definition which is captured by a formula of a set. Okay? This is also a notion that many mathematics students who are not taught set theory ask, what is a class? What is the difference between a class and a set? Okay? And this is a very valid question. And these are some of the reasons that it is necessary to teach some logic to mathematics. Okay? In fact, I'm not boasting. I have left IISER 3 years ago nearly. And now I was conducting interview for NBHM and such, and a whole lot of IISER students came. And then they said, yes, sir, we are missing you, sir, because now whenever we ask our teacher, what is a class, they say, go and ask HMS. Okay? It should not be, even a place like IISER, it should not be in this. Okay, so let me come here. Now, so by the way, I stand corrected. This is piano arithmetic for second incomplete. So I have introduced a notion, a binary predicate of integers, natural numbers. What is it? Mn satisfies this predicate if and only if M codes a proof in a formula of coded by N. Okay? And the theorems of N are precisely those for which there exists a M, there exists a proof. That means there exists M, proof T, Mn. So that is a unary predicate in N. R is the set of all codes of theorems of T. Now, representability theorem we have I taught, I said that only a predicate is recursive if and only if is representable if and only if it is recursive. Okay. So instead of starting with set of all theorems, which becomes a, as you have seen by first incompleteness theorem, now you know an example of there can be a semi-recursive set which is not recursive. I have started with a recursive predicate. Okay, because corresponding to this, I have a formula that represents it. Okay. So by representability theorem, there is a formula phi xy distinct in the definition of representability it is, such that phi with xy represents this predicate. Now you know the definition. Okay? So essentially, you may think of this as syntactical counterpart of this predicate in the real world. Huh? This jumping from natural language to formal language is one of the masterpieces in mathematics invented by Godel. I meant it and I will stand by it, that it is one of the masterpieces in mathematics. So,
sir, why phi has only two free variables?
Because of the definition of representability.
But there were, I think, free variables were more.
Well, I'm telling you that this is precisely because if you substitute only kn here, and if it still it is some more variables are left, then there is a problem with the definition. Okay, so this is how representability is defined.
Yes, I will look it again. Yes.
Yes, that is how it is defined.
Okay.
You can also imagine that, it is logical. I mean, it is natural. Huh? Because what am I saying? If this holds, then that should imply that we replace x by km and y by km.
Oh,
that
yeah.
guy
yes.
gets,
Yes, yes, sir. Yes, sir.
Okay. Now, you have been told by Amit Kumar that a theory is consistent if and only if there is a formula of T which is not a theorem of T. Okay? This you know. Now comes another masterpiece. You see, I am going to state you a theorem in words. And you will just see that, oh, how the hell does one put it mathematically? I'm saying that ZF is consistent is not a theorem of ZF.
So can you repeat?
ZF, the statement ZF is consistent is not a theorem of ZF. Is it a precise mathematical statement? Because, can I put it precisely? To show that something is not a theorem of ZF, I have to express that by a formula. But this is a meta statement. This is a statement about a theory. Okay? Therefore, ZF is not a theorem of T. Oh, sorry, ZF is not consistent. Has to be expressed by a sentence of ZF. Okay? So I'm doing it for T. So this will give me a clue. If there exists a formula, so there is a existential quantifier, which is not a theorem, that means which does not have a proof. What happens suddenly? So look at this. God will define the sentence. Con T. This is a standard terminology by now. So some of you may have heard of con ZF. And if my memory is working right, I think BVR once said con ZF. So con T, this means that T is consistent. Try to read it, but actually I'm just defining a sentence. This sentence. Look at this sentence, what it is saying. There exists Y. So think of this Y as there exists a formula with code N such that whatever X you take, that is not a proof of Y. Okay? Okay? Because this formula represents that X is a proof of Y. And just see, I mean, you may not have seen nowhere in mathematics you may have seen like this kind of, translation of meta-mathematical statement as a mathematical statement. Okay? My whole thing is very precisely defined, formulae, this, that, so on, variables, language are fixed and such. Therefore, this part is precisely defined. It is a closed formula, so sentence. And this sentence is referred to as con T. Okay? And meaning that, what we mean that we want to express the meta statement T is consistent by a formula of T itself. Okay? And this is magical. I mean, just tell me, have you seen such a subtle counterpart in mathematics? I have never seen such counterpart. A closer look will show you that con T, this is my statement, is a syntactical translation of the meta-mathematical statement T is consistent. The moment you ask, can ZF prove its consistency? The first thing where you will get a jolt is that, how do I make it into a mathematical theorem, a mathematical question? Because ZF is consistent, is a meta-mathematical statement. Okay? And the genius of Gödel is, whole thing is seen now here. And I have stated it wrongly, as I said, it should be PA. Second incompleteness theorem says, okay, at the moment, let me see. The way I have stated is correct. Because I will tell you general version, but here ZF has the property that piano arithmetic has an interpretation in an extension by definitions of ZF. Just now I was describing you natural numbers. And then axiom of infinity describe for me, madam, describe for me set of natural numbers. Okay? And on that set of natural numbers, the axioms of set theory are so arranged that all the piano axioms are satisfied. Okay? All the piano axioms are satisfied. Now you will say that how does this induction thing comes? That Okay, take any non-empty definable subset of integers. Here at the moment, definable is not that important for what I'm going to say. It has a list element. And that is where axiom of what is called axiom of foundation or regularity axiom. It says that there exists no sequence of sets xn such that x1 belongs to x0, x2 belongs to x1, x3 belongs to x2, and so on. In other words, if you think of belongs to as less than, then there is no infinite descending sequence. Okay? And I told you that belongs to is interpreted, less than is interpreted by belongs to. So, according to the Germelo-Frankel axiom, there exists no decreasing infinite, strictly decreasing infinite sequence of natural numbers. And that is same as saying that every non-empty set of natural number has a list element. Okay? Now, not decidable means neither ZF is a theorem, neither con ZF is a theorem of ZF, nor negation con ZF is a theorem of ZF. Okay? Well, this gives certain license to mathematicians. Nobody will be able to prove ever that ZF is inconsistent. Okay. It is also true that nobody will be able to prove that ZF is consistent. So you assume whichever you like. So mathematicians assume ZF is consistent. That is an assumption. Okay? And assuming that ZF is consistent, rest of mathematics begins. So actually, in very strictly speaking, all mathematical theorems are relative consistency, meaning that if assuming ZF is consistent, this is a theorem. Okay. Now, for example, you have already heard Vivek saying that Gödel built a model of ZF where axiom of choice holds. Well, how can he build a model of ZF? Because if you can build a model of ZF, then you are proving ZF is consistent. So he assumes that suppose ZF is consistent. Okay? Assuming ZF is consistent, now he builds a model of ZF plus axiom of choice, or ZF plus generalized continuum hypothesis, which I have stated to you, that for all infinite cardinal lambda, successor of lambda is equal to 2 to the. Okay? Again, you will see that he has already said that there cannot be a set model of Germelo-Frankel set. So what he does is that he builds a class. Okay? He builds a class, and in that class he verifies ZF axioms, and in that class he verifies axiom of choice, generalized continuum. But you will say, what is a class? Class is just a formula. So he defines a formula. Defining a class means gives a formula, phi x. And relativizes all the axiom, all the things that he wants to prove. Axioms of ZF, axiom of choice, generalized continuum hypothesis to this class. And I have already used the word relativization. Whenever you say there exists X, you say there exists X phi X. That means that X is in, there exists X in the class defined by phi X, blah, blah, blah. Or whenever you say for all X, well, once I say there exists X, I don't have to say because for all X is the defined symbol. Nonetheless, whenever you say for all X something, you say for all X, phi X implies that thing. That means take any X which satisfies phi X. That means take any X in the class defined by phi X, corresponding formula is defined. And that is the corresponding thing is everything is relativized at each X. You only talk of formulas relativized to phi X. And any such formula is a theorem of that X. That is what it is. Okay? And let me tell you a fact that I know, many people know, is after Gödel completed this thing in Europe, logic work, to incompleteness theorem, he moved to Princeton. And then he took up the question of consistency of axiom of choice and generalized continuum hypothesis and so on. And he worked extremely hard and got hold of this formula phi X. So this involves a lot of technicality and came out with it. So this class of his is called class of universe of constructible sets. And there is a standard notation, capital L. Okay, for that. And he had to walk on a knife edge because there were so many technicalities that he had to be extremely careful and check things. And in his own words, he had never felt, this was the hardest problem. And he had to think so hard, work so hard, that broke his. Okay. So anyway, this part was done in Europe. Unfortunately for me, I have only stated the theorem for ZF. And so in particular, it gives a sentence of ZF, which is con ZF, just now I described. Neither which is a theorem of ZF, nor the negation of that theorem of ZF. And this is what I am saying. So what is mathematics? Okay, mathematics is founded on Zermelo-Fraenkel set theory, maybe with choice. Okay, so here by mathematics one means ZF. And ZF can't prove its own consistency. That means con ZF is not a theorem. Okay, I have proved it for ZF, but this theorem is true in more generality, and if I had written it yesterday night, I would have made a mistake. So it says that if T is a finite axiomatized theory such that piano arithmetic has an extension by definition in T, then again con T can be defined. Then con T is not decidable in T. Okay, that is the general form. But this is what people are very satisfied with because, this is where interest lies. There was a doubt when all this, in the beginning of 20th century, when this lot of paradoxes and such started coming up after the invention of descriptive or development of descriptive set theory, of set theory by Cantor, that there was a doubt that is mathematics standing on the firm foundation, logical foundation? Is there an inherent inconsistency in ZF, in mathematics? Okay, and that was the most. That is why many big players in mathematics got into this act. And this became a number one problem at that time. And this is the message that, okay. So I am complete with the, by the way, fortunately, there is no third incompleteness. Because this itself, I can assure you that I was also, I mean, this was a very, very hard, very technical. Huh? And this is where the story of incompleteness theorem by Gödel ends. I have, in my limited time, I have tried to give as close an overview proof as possible. Okay? So before I go to my next slide, which is now something different nature, I will invite questions. So let me stop sharing. Three minutes I will wait. Because there should be questions.
Sir?
Yes?
So this definable set notion that you defined, so if I restrict it to say natural numbers, then
Yes.
is it related to recursive set notion by some way?
This is called arithmetical sets. Suppose you only use formulas starting from atomic formulas and not and one atomic formula, and then close it under quantifiers, bounded and quantifiers only, then you know that all those things are recursive because atomic formula define recursive sets. But if you take all formula, then they are precisely called arithmetical sets. Okay? Because suppose you take an open formula, phi x y, and look at the formula, there exists y, phi x y. Okay? Now set of all mn such that phi mn holds, precisely phi kmn kn holds, is a recursive set. And now you are doing a projection. So you are going to semi-recursive set. Okay? If you look at its negation of semi-recursive set, you can show that that is defined by for all x phi xy, or for all y, whatever I had used there. This. So if you look at all the sets which are defined by a formula without any restriction, then this is what is called recursive arithmetical sets. And that is the recursion theory. And let me try to show you the very next section after I do recursive function. Okay, I define, let me see, can you see here arithmetical sets?
So move a bit up. A bit up. Yes.
Arithmetical sets, okay?
Yes, yes.
And you see here, I am now using negation, if I have a collection of sets, collection of complements is negation. Okay? Then there exists for all. Huh? So if you start with, in any dimension, start with recursive sets and go on operating universal and existential quantifier, you get precisely the sets which are defined by a formula, any formula. And this is a strict hierarchy. Okay? This is called arithmetical sets, and I did add it to my book. Okay? And you will find Hollander's notations. Huh? Sigma 0n, pi 0n, so on and so forth. Okay? Here, no, yeah, here, I think. No, this is this way. Huh? So you get a hierarchy of sets. So definable sets are not just recursive. You have seen that they are precisely a kind of, I have shown you that a theorem I have proved that A is recursive if and only if there is an open formula phi. So suppose it is a K-array relation, there is an open formula phi in K variables such that N1, N2, Nk belongs to A if and only if phi Kn1, Kn2, Kn, N1, N2, Nk. So I should not use K. L1, L2, L1, L2, Lk belongs to phi if and only if belongs to, madam, hey, madam, can you take the telephone away from here? Can you take my telephone away from here? Okay, so recursive sets you get only by open formula. Okay, and that is why it is closed under negation, disjunction, and so on and so forth. Otherwise, you will get higher and higher. By the way, this is the beginning of my subject, descriptive set theory. Okay, that means sets which can be defined, which has a description by a first order formula. By a first order formula, that is recursion theory, recursive hierarchy. Okay, and you will get a real kick out of it if you see my book. And in chapter 2, there is a section called definable sets. And there are beautiful questions. For example, one of the landmark result in definable sets is the following. That is set of natural numbers a definable subset of set of rational numbers. So how do I see? Set of rational numbers is a model of, is a field. So it is a model of field theory. So is there a formula in one variable using with one free variable in the language of field theory such that a rational number x satisfies that formula phi if and only if x is a natural number. Okay?
Yes, sir.
And answer is yes. And you all know, if I ask you, who was the greatest logician of all the time? By now you will tell me maximum vote, or probably all the votes will go to Godel. But has this question occurred to you that who is the greatest lady logician ever? Okay? In my opinion, this is my opinion, the greatest lady logician was Julia Robinson. She was a student of Tarski. She didn't come, she didn't have much background in mathematics, so she went to work in logic. And at that time, you see, Gödel's incompleteness theorem also says that you cannot determine set of theorems. There is no mechanical algorithm to decide whether whether a sentence in number theory is a theorem or not. So in that sense, a structure is called decidable of a language. And this, if you can prove that a finite theory is complete, then Gödel has shown that theorem T is recursive. So you can, in fact, the definition of so what you can see is that if you take any model, then there is a mechanical algorithm to decide whether a sentence in that language is a theorem or not. And once Gödel proved that n is not decidable, set of natural numbers, I mean, so that is why I always call it omega 0. Omega 0 is not decidable. Tarski said that, oh, are there decidable models of some theories? And then there are structures, and he didn't go for abstractness. So natural numbers, rational numbers, real numbers, complex numbers. And he proved a complex number is what? A complex number is a model of an algebraically closed field of characteristic 0. And he showed that that theory is complete. He showed that for every prime p, positive prime p, a theory of algebraically closed field of characteristic p is complete. Therefore, for example, if you take a p bar, by that I mean the algebraic closure of the field with p elements, is a prime number. You can mechanically decide whether a sentence in language of field, theory of fields, is true or not. Reals. Now you have not seen a proper axiom for reals. What is a good axiomatization of real numbers? Okay, which will leave out algebraically closed fields because R is not algebraically closed. And then a notion was introduced called real closed fields. Okay, he showed that the theory of real closed field is complete. And therefore he showed using this that the set of real numbers R is decidable, meaning that any formula of fields there is a mechanical algorithm to decide whether whether a sentence phi in the theory of fields is true in R or not. So he had come up to C is decidable, R is decidable. Gödel proved that N is not decidable. Then only a structure left for him was Q. That is there a mechanical algorithm to decide mechanical algorithm which will decide whether a sentence in the theory of fields is true in the model Q or not. He had no clue. And anyway, I don't know what he saw in Julia Robinson, that he gave this problem to her. Okay? And she had to develop a lot of Diophantine number theory herself. She had to discover, come out with a formula, which will characterize formula of field theory. That means you are only allowed to use plus, minus, multiplication, and so on. Which will characterize natural numbers among rational numbers. Okay? And this is a remarkable result. And by the way, I cannot read the proof of it because it requires a huge amount of number theory, very sophisticated number theory. Roughly speaking, very roughly speaking, a rational number in its lowest form is integer if and only if denominator is 1. Otherwise, what happens? Look at the complement. That if it is a positive integer, then there will be a prime p that will divide it. Now, it is not that the rational numbers are given to her in the form m by n. Okay? So, just the concept is there. So, she has to translate that whatever possible denominator could be, that is not divisible by, that does not have any prime number as its factor. And that brought into p-adic fields into the picture. And she had to prove an enormous, a very difficult theorem. And when I was learning this, I learned it from a book by, I saw this in a book by, what is his name? I'm forgetting. So that was the standard book. And it is given as an exercise. And what he does is that he writes down a formula that defines n. Then I said, oh, once you are given a formula, it is easy to check. Oh my God. To check that that formula is satisfied by a rational number, if and only if that rational number is an integer or a natural number, requires very deep number theory. And I was just not able to get it. And I say, what? If your formula is given, then what is there? Now let's see what are the things that it defines. No. And then I learned the whole story. And then I went back to the original. And then I said, oh, I have to become a number theorist, an expert number theorist, to show that that formula defines set of natural numbers inside. Okay. So this was the question sparked by Dhruva asked me that are these all recursive sets, definable sets? So answer is no. And very good question you have asked. Thank you for this. It gave me opportunity to tell you many things which you should know. And,
yes, sir. Thank you so much.
And it will make you appreciate the logic. And by the way, as Ranjan Babu says, and he is correct quite a bit. I'm not a logician. I'm a mathematician first. And for me, what fascinates me most is how logic and set theory hits mathematics. Okay? So I work in the intersection of mathematics and foundations of mathematics. Okay? And because of this, the advantage is that what is beautiful in this strategy is that you learn a lot of mathematics, variety of mathematics, because they are applicable in variety of branches of mathematics. Okay? And, you know, my main fuse हो जाता है as soon as I see that something has no contact with me. Okay? So if Ranjan Babu wants me to learn intuitionistic logic, there are two things he has to do. He has to show me the application of intuitionistic logic in mathematics. And he has to show me at least one challenging theorem in that. With a subject without challenge is also not that interesting. Okay, any more question? Dhruvo, I think I have answered you.
Hello, sir.
I have answered you. Your question.
Sir, there's a question from YouTube.
Yes.
For you, sir?
By whom?
Shamik Paul.
I expected. Sure.
What's the difference between N and PA?
N and?
PA.
Because in N there is no induction. That every non-empty set of integers has a list element. That is not an axiom. It just gives usual arithmetical property. Okay? Successor function is 1 to 1. 0 is not a successor element. Okay? Then x plus 0 is x. X dot 0 is 0. You just look at that. What if I can use, sorry for non-Bengali speaking person, these are all party statements about numbers. You know, by party, okay, translation would be trivial statements about numbers. They are not far-reaching. Okay, you can't, without proving, without having method of induction, you cannot proceed in numbers. Okay, so that is the answer. Big difference. Yeah. Okay, so let me again share my screen, and you may say, oh, what a temerity I have. Nonetheless, okay. So since there are a lot of students, and I am an old man now, retired mathematician, I think I have earned the right to give sermon. So, in my opinion, one way to understand, okay, let us say a theorem in mathematics, is to look back at the proof and try to guess how the mathematician could have discovered the result. Okay? Great theorems in mathematics often look magical, but not to its discoverer. The discoverer must have gone through some natural thought process. And this is where his ability comes, and used his technical power to overcome major hurdles. Okay. Let me stop here and tell you yesterday was World Mathematics Day. And Manjul Bhargav spoke yesterday. Did any of you hear?
Yes, sir. Yes, sir.
There is only one mathematician so far for whom you can't guess how he could have discovered his theorem. Who is that? Yes. Don't say loudly.
Ramanujan, Srinivasa Ramanujan.
Ramanujan. Because the guy didn't give any proof. He just wrote down theorems after theorems, identities after identities. So don't try with Ramanujan. In fact, Manjul himself said that in all mathematicians, great mathematicians cases, he can say, oh, how could he have thought of, how could he have proved this? Huh? And in Ramanujan's case, he is the unique mathematician who will say, oh, how did he think of it? Okay? No clue. Okay? And in this way, Ramanujan is a unique mathematician. You have not seen a mathematician like Ramanujan. Okay? And, very recently, Maradona died. And hue and cry, everywhere in the world. Then I read the statement of the Argentinian, I think he's the president called, head of a state, a prime minister, who said that he was the symbol of Argentina. And then to my students, I sent a tweet that like Maradona is considered symbol of Argentina, who do you think will be considered symbol of India? Okay, I will come back to your answer towards the end. Keep on thinking. There is another very famous question of mine, which I sent over email to all my colleagues in mathematics and colleagues in ISI. Name 4G, capital G. Name 4G of mathematics. Okay, think of it. Okay, so as I admit that it is a temerity of me to try to guess what is the mind, what was the thought process of idea of mine is that in this way, I will be able to give you a better overview of first incompleteness. So this story is already known, and history behind it is known. This is what is sparked. So Hilbert, what is known as Hilbert's program, first it said give a finite set of logical axioms and a finite set of logical. I have used somewhat my experience to state it a little more clearly than Hilbert may have stated, because of the time factor, time gap. Give a finite set of logical axioms and a finite set of logical rules of inference on which entire mathematical reasoning stands. That means, whatever is provable, whatever all theorems can be logically deduced by them. Okay? And I'm not very sure whether he meant finite here. Nor is it true. You have finite schema. Like propositional axiom is even if you confine yourself to countable language, they are countably infinite many thing. So it is a schema. So probably this finite thing is I should not have said. And this was the first thing that Gödel attacked. And proposition, now completeness theory. Okay? And the beauty is that whatever is semantically true, whatever is a theorem due to mathematics, is syntactically true. Based only on finite schemes of logical axioms and logical rules. Now, it's magic. How did you guess? My only answer is that, well, all these are tautologies, and here, whatever you are inferring is a tautological consequence of whatever you are assuming. Infer this from this and this. So if you put all them theoretically, okay, and then you start proving. You have not been shown the proof of propositional of the completeness theorem, but again it begins in a very natural way that only syntactical objects are there. So he has to only build his model from syntactical objects. What could be the elements? Well, only thing that he can think of are variable free terms. Okay? And on that variable free terms, he starts in a natural way building a model. And maybe back forth, this, that. He said what are the logical rule, axioms and logical rules have been used in the entire proof, and he may have come to this. Otherwise, to start with first is impossibility. Okay? But this I am not able to explain you more because the proof of completeness theorem has not been. And the second was that give a complete set of axioms for. So this is where I spoke. This was my topic. This was Amit Kubek's topic. So I will elaborate on this. Okay. Now, so obviously this is a meta-mathematical statement. It's not a mathematical statement. So he has to turn it into mathematically precise manner. So that must have, this is my guess. Or even if it is not my guess, even if my guess that this is how Gödel may have thought is incorrect, this is one way you can go back and say, oh, this is one way this theorem can be proved. Okay? Now comes, what does he mean by give a set of axioms? And I have already elaborated on it. The minimum that we require is that there should be a mechanical algorithm to decide if a statement is an axiom or not. Okay? Given a formula, you should know whether it is your axiom or it is not only your axiom. And I gave an example where I can write down a complete set of axioms, but then if you ask me the question that is twin prime problem is there, is an axiom or not, I have no way of saying. Okay? And so this is how he came to this thing. But the problem is that what is an algorithm was not defined till then. That also needed mathematicality. People only had an intuitive notion of algorithm. Huh? And then another thing is that, okay, now your objects are going to be inputs are going to be formula. Huh? So Euclidean algorithm you have seen, but this kind of weird thing as input, that also. So this is what happened. My guess. Huh? And then, in order to answer this, he said that, what symbols are there, what symbol you use, does not matter. And because for number 3 algorithm and this and that is what intuitively mathematicians understand, I will turn them into numbers, represent them by numbers. Okay? And once it does that, automatically this coding, this, that comes. And all the syntactical objects being finite, okay? Symbols have been given, symbol numbers, and therefore the finite sequence of expressions are coded by a number. And then whether it is a formula or not, it codes a formula or not, whether it codes an atomic formula or not, it codes a term or not, and so on. And he may have come with the coding. And now, once he does that, develops the theory of recursion, he says that, okay, Hilbert's question is this. So he can define the notion of finite was automatic restriction to him to arithmetize, and axiomatize just means that it should be mechanically possible that which formula is a theorem and which formula. And then he says, this is what Hilbert is asking. Find a complete axiomatized finite QET Schaefer number. Complete is here. Not finding any such T, he might have developed a feeling that such a T can't be found.
Hello, sir.
Yes.
Sorry to interrupt you, sir. There's 5 minutes left, sir. Just
yeah. No, my machine says 6 minutes, but I will not need more than 5. Okay. So he has shown this through his arithmetization. And then now comes that, that this set is recursive, may not be recursive for natural numbers. How do I show? And then he may have discovered this gem of an idea, representability. Okay? But proof representability theorem requires number theory. And he said that I would like to choose as small a fraction of number theory as possible. So whatever definition in the beginning he may have begun with recursive function may have got modified, gone back and may have got modified. Okay? Okay. So I have already talked of his impact. So if you try to think of it, so recursive function, and then develop recursive functions, semi-recursive functions, and then arithmetization. In modern days, it should not be very hard because of people are so used to writing computer programs and such. But the representability theorem is a general idea. Okay. And finding this, so what are the places where his genius is shown? First of all, defining recursive function. It turned out that so far, I mean, now Church's thesis is there. That's it. I've defined an algorithm. And he gave a very weak definition, and even that captures entire. So that is one part of it. And second part of genius is representability. Okay? The proof looks hard because you have to do a lot of tedious work. Okay? There are steps. You are developing theory of recursive function, then semi-recursive function, Gödel's arithmetization, and various things are this. These are all very painstaking hard work. It's like slogging, but it's working through an idea. So if you have that idea in mind, then it will be easy for you to sail. Okay? And this is one way you can look back. And if you look back like this, and again, like if you try to start reading the proof of completeness theorem from my book, then again there is a lot of slogging, meta theorems. But you know the goal, that I have to build a model, just assuming consistency. Okay? And then if you see a naturality, you will see it will not be that painful to learn. Okay, so that's it. My job is over, and I suppose Logic India will give me a leave now. If
Thanks
any of you,
Thanks a lot, sir. Do we have any more questions?
Excuse me, sir.
Yes.
So this is a slightly historically motivated question. So, Gödel, along with besides this incompleteness, besides these incompleteness theorems, Gödel also published a paper on Russell's analysis of Principia Mathematica, right, sir?
Did he? I don't know.
I think it was about undecidable propositions in Principia Mathematica.
Okay. No, he must have done something because at that time. But anyway, you see, that has come to a knot. Does anybody talk of Principia Mathematica now?
No, sir.
That has come to a knot.
Curious. I was just curious.
Yes. So he may have done something, but I am not aware. I thought that you will ask that he also worked in cosmology.
But can we say that influenced him somehow in finding this, in developing this proof?
I will doubt very much because I have a feeling that they were only formalizing the way of thinking. Whether they were anywhere near complete, even completeness. You see, you may have heard, first earlier philosophers whose names are still there, household names, Aristotle, Plato, and such. They were trying to develop theory of reasonings in some non-mathematical way. And the first mathematical symbolic way probably is due to, is BBO around or not? It would have been very good, his comments. Yeah. So, the first symbolic thing came by George Bull.
Yes, sir.
Okay. But it only formalized that in a symbolic way, and that too only a propositional part, Huh? And probably he ended there. I have the book, and what is it called? The Laws of Thoughts. The completeness theorem, even for propositional logic, is a 20th century mathematics. Okay? When Hilbert came with this, Russell and Whitehead started writing this memoir, trying to see how mathematicians think and all that. Okay? And I
Yes, sir.
don't think, I have not read it, I mean, this, that Gödel may have been influenced by this. I'm almost certain. He was working all alone. He was in Vienna. And from time to time, there was a Vienna logic circle. So from time to time, he will drop into Vienna logic circle. But there also, he will not take participate in the discussion over table, quietly in his own world. Huh? So my answer to your question is, first of all, I don't know precise very well. My guess is no. In logic and set theory, these are the two major works. Logic he did in Europe, set theory he did in Princeton, and well, of course he had done many other work in many other areas. But foundations of mathematics, I think these are the most significant things. Vibira, if I am wrong or if you have different views, please speak.
No, that is fine. But at that time, contemporary mathematics, there were a good logic school in Poland, Lukasiewicz and others.
Yes.
And also, von Neumann was also working in set theory and so on.
Yes.
They were similar, you see. So there was a nice environment, so to speak.
Yeah, that time it was very nice environment. No, there were many people working. Hermann Weyl was working.
Right.
Hilbert himself was working, Hilbert Ackermann and this.
Right.
So it is not that, but the real, real push, I would say. I mean, you cannot, the only place where he failed is to prove independence of continuum hypothesis, an axiom of choice. The only place where it failed. So he showed that they are consistent, but their negation is also consistent. He did try, but he failed. Okay? And that shows the power of Cohen, who could give a model. And Gödel was obviously the first person to whom Cohen rushed. And by that time, Gödel had become very recluse. And the story, and I have read it at various places, that he goes to Gödel's office. Gödel quietly, little bit opens his door, takes his paper, and shuts the door. Okay? And after 5 minutes, he opens the door and gives him Gödel and says, "It is good." Okay? So I'm sure he followed within 5 minutes what Cohen has done. And unfortunately, Cohen himself didn't pursue his technique, which is the bread and butter now of set technique called forcing. Okay. Chairman, sir. Mr. Gokul.
Yes, sir.
छुट्टी दे रहे हैं?
Yes, sir. I'm here, sir.
अरे छुट्टी दे रहे हैं?
Yes, sir. ठीक है, sir.
So if there are no questions, thanks for your patience.
We thank you, sir, for spending 5 days.
Yeah.
The last 6 days. Sorry.
Thank you.
Okay.
Thank you so much, sir. Once again, thank you so much.
Yeah. So I will be just keeping it on, and but again today also I have go, but I think I will drop it. Now is whose stock? Now is BB house stock. Yeah. So I will drop it sometime. Yeah. Yeah, I didn't take too long. If you are really motivated, I will. Oh, by the way, yeah, one or two more things I have to say. I wrote an article long time ago in Resonance. Transfinite numbers, what is infinity? And this is what Madam presented. And for beginners, I will strongly recommend that. And of course, you will find what she has done in I mean, the same thing is reproduced here in my book on course on Borel sets. So I can give you the reference. It is resonance. Please write down SM Srivastav, transfinite numbers, what is infinity? Resonance, I think volume 2, number 3, and it was in 1997. I'm very proud of this article of mine. And I would particularly the beginners, beginning BSc students and such, I will strongly recommend this book. Okay, this article of mine. Though you can read it from my book. And if you are interested in, if you have become motivated in logic, of course I will recommend my book. And who said that? Oh, we download it, Rana, no? So I hope you can download it easily and try to read it. Yeah, I have nothing to say.
Hello, sir.
Yes.
Sir, I want to remark that Gödel also had a model of universe called Gödel universe and solved some Einstein field equations. So he has some important contributions to physics also.
Well, that is what I was saying.
And
that is what I was saying in cosmology. You see, he showed that in theory it is possible to have time travel. You can travel back
yes,
to
sir,
time.
yes.
Okay?
And sir, another thing.
No, wait, let me tell you. I am now in cultivation of science, where physics and chemistry is the major subject. And even as recently as now, I heard a talk by a person from Britain who was explaining God exists. And I became very curious and I started asking my friends in there, then why don't you build a time machine? And they said, I mean, it's impractical. Okay. For example, there are algorithms to decide whether a statement is true in field of complex numbers or not. Okay.
Okay.
But you know, I mean, writing down that algorithm, I don't know. I mean, then why not just write down an algorithm once for all? Forget. You don't have to work. Whenever there is a first order statement comes, feed in there and wait for computer to give you the answer. So these are theoretical results.
Okay.
And there is a question of practicality. And now you see fast and fast and fast computers are being discovered. Data science, this. It is just because of thing. Like Turing machine has an infinite state. That means it does not assume, it does not assume that there is any space problem. But every computer has a space problem. It does not. It does not assume time problem. But no.
Okay, sir.
Oh, so many thanks. Who is this Ranjan Babu? Ranjan Babu is the first to thank me. Haha. Thank you very much. Thank you very much, all of you. Thank you very much. It was nice seeing you. Well, I would have liked to see somehow camera was muted to see the face. Huh? Thank you very much. Thank you very much.
Sir, one more thing.
Huh? Yes.
Sir, you told that Bhopal was the first to use that forcing technique, right?
Yes.
But I read from some source that Sharon Shella was also the founder of forcing technique.
Not the founder. He is now the biggest expert. But there are many big experts. There is Udin, there is this. Now it is very well understood.
Okay.
Yes. He can be regarded as the best model theorist now. He may be even regarded as the best set theorist now. But there are lots of debates, you know. Okay.
Okay. Thank you, sir. Thank you.
Yeah. Okay.
Sir,
Bibio, you take the stage now, Bibio.
Okay. No hurry. No hurry.
Thank you, sir. Now we pass on this session to BV Rao, sir.
Can I take a minute?
Sure, sir.
Yeah, so I'm going to circulate a feedback form and I request all the participants to please submit your honest feedback.
Okay, Amit, you reminded me. I will send now my file and madam's file.
Yeah, I will update that.
Yes, and so that the typos are removed.
Sure.
Okay. Okay, Bibia.
Okay.
Yeah, 5 minutes into this lecture, I will share something in the chat. Please fill that up.
Okay.
Thanks a lot.
Okay, sir, we can start the lecture, sir.
Okay, thank you, Gokul.
Thank you, sir.
Okay. So, welcome to all the participants. I think you should feel relieved because after this lecture, you are now completely free. Okay. So, generally I was not preparing slides. So today I have prepared. So last few days we were discussing about axiom of choice, ordinal numbers and so on. And there are a couple of theorems in the notes we have not done, but you can see nothing profound. Okay, I will start with a quote from Harish Chandra. I have often pondered over the roles of knowledge or experience on the one hand and imagination or intuition on the other in the process of discovery. I believe that there is a certain fundamental conflict between the two. Knowledge, by advocating caution, tends to inhibit the flight of imagination. Therefore, a certain naivety unburdened by conventional wisdom can sometimes be a positive asset. Okay? So, you should be able to think, not be afraid of, all the disasters that you may have if you don't obey rules and so on. Okay, so today what we are going to do is the following. Okay. We will discuss axiom of. What happened? What happened?
You shared the wrong window, perhaps. Yeah.
Okay. Yeah, I shared the wrong window. Okay, fine. Okay. Yeah. We will discuss about axiom of choice, continuum hypothesis, and I have named this lecture as Folksy Alap. The Folksy refer to folk song, Alap refers to classical music. So Both are good. If you listen to Bhupen Hazarika, it is different from listening to Bade Ghulam Ali Khan, right? But both are great. And a folksy thing gives you a preview into the classical thing. So in the same way, I will not be rigorous, but however, I will try to explain the idea of certain things that have gone on about the continuum hypothesis and the axiom of choice. But before I even start anything, let us look at, I want to understand our thought process. Suppose you take the theory of groups. Somebody says for every x there is a y plus y equal to x. Okay, I am looking at group with addition. How do you decide whether this statement is true or not? Of course, most of you would say, let me look at integers, that is a group, but 3, if I take x equal to 3, there is no y satisfying this condition, therefore this is false. That is because we have become expert. Many times, when you understand mathematics, you forget that you are an expert. Imagine that you are a naivete. Okay? So this naivety is something very important. If you don't know, how are you going to go about it? Okay? So let us say we started with real life as an example of a group. Then what you would think is the following. Let me see. I know real life is a group, but can I see what is the smallest subgroup kind of thing which will help me to understand? Okay? I will try to put the needed elements in the group. I will find out whether x by 2 is needed or not. I am loosely using the term x by 2. Don't worry. That means a y such that y plus y equal to x. Okay? So, is it needed or not? If you took the subgroup 0, then you say, no, that won't do. Let me take 1 also. So look at the subgroup generated by 0 and 1. Then you come to integers. Okay. And now you see that this statement is not true. Okay. Of course, you might say, come on, you complicated my life. I already said integers, but you said you went to real life. But please carefully understand what I said. Okay. Integers is because we have become an expert. Okay. Of group theory, you knew integers form a group and so on. But an analyst starting from real life, how does he go? So you find out, if I take the group which consists of only the needed elements, I would know whether x by 2 is needed or not. I am using the term x by 2. Okay. Now, whenever you say there is a y plus y equal to x, what is your mental picture? Your mental picture is y is x by 2. That's all. I am using my mental picture. There is no y, there is no 2, and so on. Okay. So that simply means this one. So integers does not have. Therefore, it is not necessary for this to be true. Okay. But how do you go to integers? You know, of course, you might think that I am underestimating your knowledge. Please, it is not underestimating knowledge. It is understanding what we have been doing. Okay? You do several things inadvertently and you don't know what you are doing. So, let us try to see, how did you get the group containing 0 and 1? Remember, I was looking at real life and I wanted to get a subgroup which has only the needed elements. Okay? If I take only 0, it is useless. Therefore, I took 1. What else is needed to make this a group? Of course, I am looking at additive group, as you can see. I take f1x is equal to minus x and f2xy is equal to x plus y. Why am I taking this? Because this is not a group. Why is this not a group? Minus of an element is not here. And sum of two elements, 1 plus 1 is not here. I have to put them. So I take these two things. And then I will get add them to my set S. Sorry, this is not S, this should be L0. Okay. So for any set S, if it is not a group, you can define a new set, namely your set along with minus of points in your set along with sums of two elements in your set. That will give you a new set. I start with this. I look at the new set f of L0. Is that a group? No, that is not a group. You can clearly see. Therefore, I look at L2, f of this L1, and so on. In general, Ln is f of Ln minus 1. I take all these things. Then I say G equal to union Ln. This is a group. Okay? And I am sorry for saying something which is probably below your standard, but you will see the beauty if you analyze your own constructions, okay, your own thought process, you can do well. So this is the thought process in getting integers, okay. And of course, somebody can say, okay, ordered fields. It is a field where there is an order satisfying those axioms. I shall not go into. Somebody asked, is it necessary for every x positive there is a y into y equal to x? That is there a square root? Of course, you can quickly say, no, rationals. Okay. But let us see what is the process involved. Again, if you are not an expert, if you just know real numbers, if you know analysis, if you are at a wrong junction, how do you go to the right junction? Okay. So again, you start with 0 and 1. And you try to make the smallest field, okay, that will tell me whether square root is needed or not. And in this case, of course, I will not explain too much. You have to put two more functions, namely f3x equal to 1 by x, and it is not defined if x is 0. f4 of x comma y is x into y. Now you should take fs as, for any set S, f1s, f2 of s cross s, f3 of s, f4 of s cross s. Put all those four. That will be f of your set. Now you start with L0 and then look at L1 exactly. Then you look at union Ln, that will be a field. You got the set of rationals. Okay. There, this is not correct. Therefore, this statement need not be true. Okay. So what is the thing? The basic thought process is, let me see if it is needed. Okay. The concept needed is not mathematics, but don't worry. Now, what are we considering now? Is there, okay, there are two things, axiom of choice and the continuum hypothesis. I will try to stress more on the continuum hypothesis. Okay. Then I will talk about axiom of choice a little bit. Is there an infinite subset of R neither in correspondence with Z nor in correspondence with R? Okay. Correspondence means one-to-one on-to correspondence. So let us not. This is the question. Okay. So how do we attack it? There are two ways, semantic and syntactic. Of course, you have been listening to models and logic and so on. So all of you know the meanings of these words, but just to stress upon you and quickly recall what you have been learning, syntactic means the following. Axiom, B.B. Rao of CMI is an idiot. Axiom, all idiots have two hands. Inference, so B.B. Rao of CMI has two hands. Okay, absolutely nothing wrong. Because from these two axioms, this inference follows. Okay, you don't care about the meanings. You care about whether a certain statement follows from the axioms or not. Okay, and semantic means I say this model, namely picture of B.V. Rao of CMI on my screen. He has two hands. Okay, please let me remind you, you are not seeing B.V. Rao. You are only seeing the picture of B.V. Rao, a model. It is quite possible that not all of you are seeing the same model. Okay, it depends on your internet speed, on your laptop, various things. So you are seeing only a model. Okay, this is semantic. So, first, semantic is something, it is a picture. Therefore, let us discuss the semantic aspect of it, okay, of this question. Is there an infinite subset of R? So, let us try to see. All right. So, I want to build a model of set theory. Suppose I try to put only the needed sets in my model. Would it allow such sets which are not in correspondence with Z or R? Okay. If I put only the needed sets, okay, I put sets in my bag so that this bag forms a model of ZFC, and every set here is needed for it to become a model. Then, if such a set contains a subset of R, which is neither in correspondence with Z nor in correspondence with R, I believe probably such sets are needed. Therefore, continuum hypothesis is false. But if my model has no such set, I have got an answer. Okay? So this is the idea. So how do I do? Absolutely nothing wrong. You can also do it. Okay? Gödel has done it in 1938-39.
Hello, sir.
Yeah.
Sir, can you repeat the last part?
Yes. The last part is the following. You see, what is the philosophy? I want to build a model of set theory, okay, putting only the needed sets. What do you mean by needed? Only sets in my bag I put, which are essential for the bag to become a model. Okay, that's it. Of course, we have to make it clear. Right now you will wonder, what the hell you mean by needed? What the hell you mean by bag? Okay? If you are leaving out some sets, how can it be model? Of course it can be model. In the real life, we have left out certain numbers, but what we have collected is a model of group. What we have collected is a model of fields. In the same way, the collection of sets that we have in our bag will be a model. Is it okay? And some
Hello,
of you...
sir. Hello, sir. Sir, is it like, suppose you delete few axioms from GFC, then there will be a class of sets that can be created by the axioms, right? Is it like that?
You see, don't try to make everything precise right now. Okay?
Okay, sir.
As I said, with this initial thing, okay, this is how you should think. Knowledge, by advocating caution, tends to inhibit the flight of imagination. Okay? Please, you should never, okay, forget this flight of imagination. Okay? You must remember, if you have not read, how Einstein thought that we cannot travel with the speed of light. Why? Because Michelson and Morley have conducted experiments. No matter how they measure, they are getting the same value. Okay, I don't go into the details. Then Einstein thought, wow, suppose there is a photon traveling. I travel on a photon, sitting on a photon parallel to it. If they are going at the same speed, obviously the other photon should look stationary for me because we are going at the same speed. Okay. Therefore, obviously I cannot. Okay. Now, this is a stupid thing. How can you sit on a photon? How can you travel? Okay. But don't worry. Imagine everything you can. Okay. Therefore, in the same sense, is it okay? But once your thought process has come to a thing, you try to make it precise, right? But sorry, I forgot your name. You are absolutely right. I am talking about a class, okay? But you already thought about the class because you knew about the class, okay? But let us not think. Let us go by our naivete, okay? That is very important. You know
Yes,
that,
sir.
okay? Yeah.
Yes,
But
sir.
you are absolutely right. Okay, absolutely. I don't want to stop your thought process. Please do think. Okay, but don't let it be corrupted. Okay, by too much precision. Okay.
Yes, sir.
Precision will come later. Thought process will come first. Okay, and if you are worried about precision in the beginning, your thought process stops. Your imagination stops. Okay. Yeah, but you are absolutely right. Let me tell you that.
Hello, sir.
Yeah.
So what I wanted to know was, suppose you deleted few axioms, then there are few sets that can be created by those axioms, remaining axioms, right? So you put all those sets into a bag. Is that what you're calling the?
You will see. You will see. I'm going to explain everything. Don't ask. Okay.
Okay, sir.
You will see. You will see. Okay. Now, so far I said we will put only the needed sets in our bag. So the question you are asking is, what are the needed sets? For example, there is an axiom in set theory which says if there is a set Y, if there is a set Z, then the set consisting of only Y and Z should be a set for you. This is called pairing axiom. If you have a set X, if you take all sets which are in X and take their union, then that set should also be there for you. This is called the union axiom. Is it okay? Therefore, if there are certain sets in your bag, then the axioms force that some other sets must also be in your bag. Okay? And just as if a point is in your group, minus of that, if there are 2 points, the sum should also be in your group. If there are certain sets in your bag, then these new sets should also be in the bag. So just like minus and plus, there are certain operations on sets which will produce new sets, they should also be in your bag. Therefore, I start with a collection of sets. Okay, in the group case, we started with 0 and 1 because we wanted to build a group which contains 0, but 0 alone is useless, so we put 1. Now, I start with empty set. Why? It is an axiom. Empty set should be there. And the set consisting of empty set should be there. Therefore, U1. Therefore, if a collection is there, f of that should also be there. Therefore, I define, starting with this, remember, I want you to look at that L0, L1, etc. I want to see that exactly imitation is the name of the game, nothing new. But execution is different, very complicated. Okay? Therefore, I look at f of this. Similarly, f of this. In general, I look at u alpha as all beta less than beta, u betas. Oh, sorry. Oh, I should have, there is thing here. F of this union u beta. Okay, there is an error. U alpha is f of union u beta. Okay.
Hello,
and
sir.
my model is all the u alphas put together. And again, I want you to look at the model of the group is all the L's put together. Okay? Therefore, just as I am building a group starting with 0 and 1, I am building a bag of sets starting with empty set. Exactly the same process. Okay? Now, there is an error here. Please remember, this is f of union beta. Okay? So, this is the previous class we have got, and take f of that. That is u alpha. All the sets together should form a model. This is the idea. This is the imitation. Is this idea correct? Will it work? The beauty is it works and over. No more. Who proves it works? Gödel proves it works. Okay? But I will explain the same thing in a different way so that certain things can be easily visualized. Okay? Let me take L0 is equal to empty set. If you have defined a collection L alpha, then I define L alpha plus 1 as the collection of sets that can be defined using these. Everything that you define should be there in your bag. Okay? If you have 2 sets, then anything that can be defined in terms of the 2 sets should also be in your bag. Okay? You will ask, what the hell do you mean by defined? Okay. Now we come to this thing. Take a formula of ZF. It has free variables x1, x2, xm and y1, y2, yn. Take any sets a1, a2, an. Okay. In L alpha. Look at the following set. What is that set? it is all M tuples in your L alpha for which the statement phi of B1, B2, Bm, A1, A2, An is right. In other words, this is the collection of all M tuples for which this formula is correct. When you put the parameters A1, A2, An for y. Okay. So this is a set that I can define, okay, using already existing sets in my bag. L alpha is already existing sets. This is the set of all M tuples which obey this formula phi of Zf. Okay. I am allowed to use my sets to build new sets. This is probably a new set. And for a limit ordinal, I take L alpha as union of all previous things. Okay. I look at the grand L, which is union of L alpha over all ordinals. Of course, L is not a set, but a class of sets. Now let us see. Is it okay now? We have imitated exactly the same thing. And the point is, L does form a model. Okay? And wait a minute. Oh, I see. Okay. Now, L forms a model for set theory. That is what Gödel has shown. Now, L shows axiom of choice and continuum hypothesis. Details are in the notes, but I will explain. How does L show the axiom of choice? I am going to well order the entire bag of sets. In particular, every set in my bag is also well ordered. Okay? Remember, my collection L is transitive. That is, if a set X belongs to L, if Y belongs to X, then Y is also in L. Why? Because every set I have collected is made up of the previous collection of sets. Okay? Only previous sets are collected, which the formula phi dictates to make a new set. Okay? For example, if you take a formula with one free variable, you see this M1 nonsense should not confuse you. Take a formula with one free variable, then you are looking at all B about which phi B A1 A2 An is true. That is it. Therefore, if I well order the entire L, then the entire universe is well ordered. In particular, every set is well ordered. Okay? Now, how do you well order L? Well, if you well order each L alpha, you have well ordered entire L. Why? Because if you have well ordered L alpha, how do you well order L alpha plus 1? I will explain. Therefore, the new element of L alpha plus 1 come after L alpha. Okay? Therefore, the order xy in L is the following. If x appears in L alpha, y appears in a later L beta, okay, beta bigger than alpha, then x is less than y. Finished. If both x and y appear in the same L alpha, how am I going to order? Okay? All right. At the limit level, there is no problem. It is the union of previous things. There is nothing new. Okay, union of previous things. Therefore, let me tell you how to order L alpha plus 1. Okay, but you see with your eyes what is L alpha plus 1. L alpha plus 1 is the collection of all such sets. Okay, the number of formulae is countable. You can write them in a sequence. And the number of these parameters, okay, that are coming from L alpha, okay. L alpha has already order. If a set has a well order, okay, W class W has a well order, okay. Compare first elements or second elements, doesn't matter. Then compare first elements, whatever. The triples have a well order, okay. And if you put W cross W, W cross W cross W and so on, one after the other, then the set of all finite sequences you will get that has a well order. Therefore, the set of all phi A1, A2, AN have a well order. Therefore, I can use that to define a well order on this collection of sets. So let me tell you, a set A phi A1, A2, AN appears before A psi A1 prime, etc. AN prime if phi appears before psi, or phi equal to psi and A1 appears before A1 prime, or phi equals psi, A1 and A1 prime appear at the same level, A2 appears before A2 prime and so on. Okay? And finally you compare A. So the sets in L alpha can be well ordered. Because sets in each L alpha can be well ordered, the set L can be well ordered. Okay? Remember, L alpha plus 1 includes L alpha. We will not change. Okay? The new sets that come in L alpha plus 1, they will be put after L alpha in that order. So that gives a well order for the entire L. Okay? In particular, every set in the collection is well ordered. Axiom of choice holds. And continuum hypothesis also holds. Why? Because you can see already from this thing, okay, L0 is a countable set. Ah, wow, it is only one set. L1 is also countable. L2 is countable. If I take a countable ordinal, if L of that countable ordinal, okay, if this set is countable, then this is countable. Why? If L alpha is countable, then the set of all tuples, now you see whatever Hymanthi did for you comes into force. The set of all finite tuples from L alpha is countable. The set of all formulae is countable. The set of all such things is countable. Okay? And therefore, the collection of such sets is countable. So each L alpha is countable. Now, if only you could show that every subset of omega appears somewhere before L omega 1, namely the first uncountable ordinal, then you are in good shape. Why? Because all the L alpha up to the first uncountable ordinal are all countable sets. Okay? Therefore, L omega 1, which is union of these things, has cardinality Aleph 1. Okay? So, when alpha is the first uncountable ordinal, then L alpha is a set which has cardinality Aleph 1. If every real number appears there, then the set of all real numbers has cardinality Aleph 1. Finished. So that is the idea of the proof. Is it okay? Some of you might be wondering, come on, nonsense. L is a class, okay? But don't worry. That is why, you see, unfortunately, worry comes for us first, before a thought. You don't allow any thought to proceed. Don't worry. We will allow thoughts to proceed, okay? Now, any worries can be sorted out. Therefore, axiom of choice and this holds, and this forms a model. That is Gödel's idea. Now, I want to tell you that von Neumann used exact same idea in 1929, 10 years essentially before Gödel, to construct a model of ZF. V0 is empty set. V alpha plus 1 is power set of the previous V alpha. For a limit ordinal, you put V alpha as this union. And if you look at V, union of all these things, that is a model. Okay. Now, why did von Neumann do this? Because he, at that time, axiom of regularity was not taken as an axiom of ZFC or ZF. Okay? X belongs to X is a possibility, but X belongs to X is something that hurts you. Therefore, to avoid that possibility, they were thinking of regularity, and von Neumann came along and said, don't worry, this is a model of ZF, this satisfies regularity. Therefore, if your previous axioms are fine, regularity is also fine, nothing wrong. Now, regularity here is easy to prove because every set will appear at some stage. Okay, you can find out the list and so on, but I won't go into the detail. I mentioned this only for the historical perspective. Okay, now, so you see, again, if something is hurting, you go back to your model of the group on the real line. Okay, we have imitated the same thing. Okay, unfortunately, to execute the details is extremely complicated. Okay, and even though I said von Neumann used the same idea, this is different. But Gödel's construction and the correction of sets L, they are called constructible sets. And the axiom, there are no more sets, namely V equal to L, is called axiom of constructibility. And the collection of constructible sets is a beautiful garden, unlike this one. That garden has a beautiful flowers, lots of fragrance and so on. Excellent structure is revealed. Okay. So I am not trying to say that Gödel's L is just an imitation of this. Okay. That is much more complicated and much more beautiful. But the idea, okay, execution. So you should take the idea and execute. Okay. Now, are there any questions now? No. Don't hesitate. If you have any questions, you can ask. Okay. Now, you might ask, oh, I think I may have forgotten one other thing here. Okay, so let me point out.
Hello, sir.
Yeah, sure, ask.
There is one question from YouTube, sir.
Sure, tell me.
The question is asked by Shamik Paul. The question is, he's asking what is the meaning of the notation B1 up to Bm inside angular brackets?
Oh, this is the set of all m tuples. Okay.
Okay, sir. He was
so
asking.
If you put the m tuple in this formula, this is correct in this model. Okay. For example, phi is the formula. Let us take a formula of two variables. Okay. X belongs to y. For y, you take a. So the set of all x belongs to a. Set of all x here, which belong to a. Okay. All those things. L alpha epsilon proves. Okay. According to the structure, this is correct. All right.
I have a question.
Are
all these models built on the idea of recursion only, or is there any other idea?
Oh, yeah, there are others. You will see that. Okay.
Okay.
Sure. There are others. Okay. Now, in the notes, I have explained the semantic aspect also. Assuming that I won't get time, I have not put on the slides. Now, let me explain the semantic aspect, syntactic aspect before I go further. What I have explained to you is the semantic aspect. Okay, I have shown you a model. Okay, and I roughly gave you the idea why CH and axiom of choice are correct here. Now, some of you may dislike because L is not a set, it is a class. Come on. Okay, good. Now, here is the syntactic thing. Okay. If you say that CH, continuum hypothesis, leads to a contradiction, that means using the continuum hypothesis, you can arrive at a contradiction. Let me get some other thing. Okay. Yeah. I want to share some other thing. Yeah. Okay. You may feel uncomfortable because this is a class. So here is the syntactic way of understanding this. With this, you should have no problem, but this has no meaning really. We define a formula phi x. What is phi x? This formula says that there is an alpha, x belongs to L alpha. In other words, phi x is true if and only if x belongs to L. So phi is a formula with one free variable. We can write it. It is a very long formula. Okay. And there exists an ordinal, and ordinal you can write down, and x belongs to L alpha. Okay. As of now, this is a formula with one free variable. One shows that for each axiom phi of ZF in the structure L, in other words, the relativization of this phi 2, okay. So I have used phi for both, okay. Small phi of capital Phi is true. What is meant by relativization? Since some of you may not be familiar, let me tell you, when you take a model, your objects are in the model. But if the model is outside your purview, you are talking about a formula. So whenever you are talking about a formula, okay, of one free variable, in your mind, please keep all x satisfying this formula as the model. That is not a set. That is in your mind. But I will not depend on your mind. Okay, I will explain. I will now take this formula. I will define relativization. How do I define relativization? Suppose phi is there at this x psi x. Then what is the relativization of this? Unfortunately, I have used phi for both. Please, this capital phi, I will denote by L. Okay, I will read it as L. Okay. There exists x psi x. There exists x, Lx and psi x. That means when the formula says there is an x psi x, I change it to there is an x such that x is in L, Lx and psi x. Similarly, if the formula says for all x psi x, then its relativization is the formula for all x, Lx implies psi x. Please, I am only telling about the formula. But if you keep the model in your mind, what it says is the following. If the formula says there is an x satisfying this condition, the relativization says there is an x which satisfies the extra formula L and satisfies the condition. And if the formula phi says for every x psi x holds, then this relativization says for every x in L, that is for every x which satisfies Lx, psi x holds. Okay. In other words, this is the relativization as you would think when you apply to the model. But this is defined independent of your model. Okay. So for every formula, I show this relativization defined. And here is the upshot. I am going to show that relativization of the axiom of choice holds. Then why should you accept my proof? Because the reason why you accept this is the following. You first show that under relativization, I have made a mess now. Okay, as long as you have a model, your eyes have a feast. But when you don't have a model, when you have a formula, you are lost. Okay, therefore, let me tell you, you close your eyes, there is no model, think about it, there is a formula L, okay, in your mind now. All relativizations of the axioms of ZF are true. Rules of inference when relativized are true. AC when relativized is true. Okay, I will prove all these things. Okay, I will prove that if you take any axiom of ZF, if you relativize, it is correct. If you take any rule of inference, if you relativize, it is correct. Okay, I will prove all this. Then what happens? If you say that CH leads to a contradiction, you can write a proof of CH using finitely many axioms ending up 0 to 1 and using AC, CH. Okay? All right? Doesn't matter, CH or AC. Okay? So if you say CH leads to a contradiction, you will write a proof of 0 equal to 1 using all the axioms of ZF and also CH. I look at your proof, I relativize each sentence of your proof. Okay? Relativize every line of your proof. Then I get 0 equal to 1. Its relativization is 0 equal to 1. Okay? In other words, I can get the same contradiction without relativizing. Okay? Therefore, yeah, sorry. I thought I may not have done, but anyway, let us see. So you see, there are two things here. Let me again repeat. You see, whenever you see, you should look at the ideas first, execution of the ideas next. Okay. So here, the idea is exactly the same thing as in the real life manufacturing the group. You start with empty set because it is forced on you. Everything you define in terms of empty set and so on, etc., etc. Put all these things in a bag. That is a model. Okay. And this model satisfies axiom of choice and continuum hypothesis. If you dislike this, you can write instead of L, okay? You write a formula 5x. That formula expresses x belongs to L. We can write one formula without using the letter L, without using this picture. But that formula, if you understand, it says 5x happens if and only if x is in L, okay? So, for example, if I say pen, it is an English letter P-E-N, okay? But when you look at the English letter P-E-N, you understand nothing. But when you say a pen, it represents the pen. So, the syntactic thing is like looking at the letters P-E-N. And the semantic thing is looking at actually a pen. We have looked at actually the model here, okay? Now, you don't have to accept anything anybody says. You can still say, no, I don't like this model. Then the other explanation is the syntactic one. Namely, I am going to show that for my formula, I will call it Lx, okay? Lx. I will define a process in ZFC, namely relativization of every formula in the obvious sense, okay? And I will show that for all axioms of ZF, the relativization is true. For any inference, the relativization is true. That is, if phi psi leads to something, then phi super L, psi super L, that also lead to this thing. You can infer. Okay? Then I am done. Because if you produce a proof of 0 equal to 1 using axioms of ZF and continuum hypothesis, then I look at your proof. Each sentence of your proof, I write the relativization. Whatever axiom you have written, the relativization is correct. And whatever inference you have made in your proof, okay, that is correct in the relativization. Therefore, you have to accept the final statement. In other words, I have shown you how to arrive at a contradiction in ZF itself. Is it okay? So, I did not go in detail that relativization, but relativization simply means in any formula of ZF, okay, whenever existential quantifier is there, I keep on putting there exists Lx. It is in L. Whenever universal quantifier is there, I say for all L. That's all. Okay. So that is why you should accept. So these are the two methods. Please remember. Okay. Now, you might understand that we have built a model exactly like the thing. You may think that you may build a model where negation of continuum hypothesis holds also following some similar principles. Namely, you can write down a formula like L. Can you get a formula psi x such that the class M of all x for which psi x is true forms a model of ZF plus negation CH? This is the natural question. Okay, the class M of all x. And one great man, J.C. Shepherdson, during the 50s, made intensive study of inner models. What are inner models? They are standard transitive models which include all ordinals. What is a standard model? The standard model is a model where the epsilon is the usual belonging to of your ZF. That is what we did in LF. We never said A belongs to B means the following. It is the usual A belongs to B. It is a transitive model. That means if in ZF X belongs to Y, in my model L, X belongs to Y, the same. And not only that, if X is in my model, Y belongs to X, then Y is also in my model. Then Y is this is transitive. And my model includes all ordinals. You can verify that all ordinals are there in L. Therefore, such models, standard transitive models, which include all ordinals, are called inner models. So he's made a deep study of these inner models, and then he said, no, you cannot get a formula psi x such that the class of all x satisfying that formula forms a model of ZF plus negation CH. Okay, this process stops there. Actually, the reason is also very simple. Okay, because whatever is true in the theory of groups must be true in any one particular group. Okay, whatever is true in ZF must be true in any particular model of ZF. But here, L is a model of ZF. Okay, so if you could prove such a thing, then if I specialize that formula psi to my L, if I collect all x in my model L, which satisfy this formula in my L, okay, that should be a model of ZF plus negation CH. And a little argument would show that is not true. Okay. Therefore, you cannot get such a formula. That is the idea. I am only giving the idea. There are no inner models. Therefore, you should look at outer models. So, I will explain outer model. But before that, just like Harish Chandra, let me read what Cohen says. In all honesty, I must say that one must essentially forget that all proofs are eventually transcribed in this formal language. Most proofs are written by epsilon, rules of inference, formula, everything. Okay. In order to think productively, please, productively, okay, one must use all the intuitive and informal methods of reasoning at one's disposal. At the very end, one must check that no errors have been committed. Please look at this, okay? At the very end, one must check that no errors have been committed. One must use all the intuitive, informal methods of reasoning, okay? But in practice, set theory is treated as any other branch of mathematics, just like a group of models, just like what we did, okay? Suppose I give you the real life and I give you the model integers. Then, if integers is your model, external model, you can extend the integers by adding one more. That's it. The reason we can do this is because we will never speak about proofs, but only about models. So therefore, let us return to what is called naive set theory. Okay. So please, there are two things here. Naive set theory makes you think uninhibited, flight of imagination. Okay. Once you do that, if you know the rigorous foundation, you should be able to formalize. Okay. All right. So I will discuss negation CH. One should start with a model and enlarge it. Now some of you would wonder, is there a model? Are we not contradicting Gödel's the second incompleteness theorem? If there is a model of ZFC in ZFC, isn't it showing that ZFC is inconsistent? You will get that doubt. Yes, absolutely you are right. Okay, there is nothing to be afraid of. Every question is to be asked and must be answered. But we believe that ZFC is consistent. And so we can work in the theory ZFC plus consistency of ZFC. Namely, in the theory, ZFC plus there is a model. Okay? You can work in that theory. Of course, you may say, no, this is cheating. Okay, all right. Then, another way is the following. Okay, all right. ZFC plus negation CH is inconsistent. Suppose you believe that. Then you say, I am going to the syntactic thing. There is a proof of 0 equal to 1 using axioms of ZFC and negation CH, correct? But such a proof uses only finitely many axioms. Okay, only finitely many axioms. The construction I am going to do right now needs only finitely many axioms of ZF. Your proof of 0 equal to 1 uses only finitely many axioms. Whatever construction I am going to do in a short while needs only finitely many axioms. Lo and behold, there are models for any finite fragment of ZFC. Okay? Given any finitely many axioms, there is a model for ZFC, for these finitely many axioms in ZFC. Okay? There is a set for which all these finitely many axioms hold. That is the theorem. Okay? And the reason ZF does not have model of ZF is because to verify that something is a model of ZF, you have to verify all the axioms of ZF. There are infinitely many axioms. You will never be able to write down a proof. Roughly, that is the idea. But given finitely many axioms, you can. So that is why I can produce a model for finitely many axioms that you have used in your proof, and for finitely many axioms that allow my construction. That leads to a contradiction. Okay. So you cannot start. So you can take this axiom, this thing, or this thing. So I would like you to understand that outer models is a good way of starting with a model and enlarging it. If you don't like, this is the other way, syntactic way. So we shall start with a model and try to enlarge it. We make up our mind to look at in transitive models containing ordinals and which are transitive. Okay, I will explain what it means. So can we start with any uncountable model? You cannot start with an uncountable model. That is the first thing Gödel realized. Why? Roughly speaking, the argument is again the same as earlier due to Shepherdson. Cohen was probably the first person who understood, I don't know, okay, forget about this sentence I made. Cohen understood what Shepherdson did, okay? And in particular, that tells you, you cannot start with an uncountable model, because if you started with an uncountable model, because we want all ordinals in our model, okay, and it should be transitive. If axiom of constructibility were indeed true, then there is no hope of proving negation CH. I will stop at this because to explain it rigorously takes some other steps. Okay. So this is the first realization. So remember, the 0th realization is you cannot imitate Gödel because of Shepherdson. Enlarge it. Again, because of Shepherdson, which Cohen understood, you cannot start with an uncountable model. So you start with a countable standard model of ZFC. Okay. Standard model, epsilon is the usual epsilon. Okay. Usual belonging to. And let us say we want to add aleph to many subsets of omega in the new model so that negation of CH holds in the new model. Okay. So we have a model M. Think of it. Okay. Again, go back. Integers is a model for group. You can extend it by adding a non-integer to get a new model. Exactly the same thing. I am starting with a model. By the way, I have slurred over certain details here. I am starting with a countable model. You can ask me, is there a countable model? There are several theorems, Löwenheim's Kolem theorem, various other things. So let us not enter into such details. We accept. I am starting with a countable standard model and I want to enlarge it. Okay. I will put aleph to many subsets of omega and enlarge to get a new model so that negation CH holds in the new model. Okay. What is the danger? There is a big danger. You can enlarge, but the present aleph 2 of your current model may actually turn out to be LF1 in the new enlarged model. Okay? Carefully understand. You have a model. In your model, there is LF2. What is LF2? In your model, you can show that this is the second uncountable ordinal number. Okay? In your model. You will enlarge your model to a new model. And you will show that there are LF2 many real numbers there. But unfortunately, in the new model, LF2 may become LF1 in the new model. That means everything below LF2 in the new model may become a countable ordinal. Okay? In the new model, if everything below LF2 becomes a countable ordinal, then LF2 will be the first uncountable ordinal there. We have not achieved anything. So, you have to make a decision. M and the enlarged model will have the same ordinals and the same cardinals. Okay? How to achieve it is a different model. Please remember, this is a thought process. We are making up our mind. We have made up our mind to start with a model because Shepherdson. Countable model because of Cohen feeling. Then we want to enlarge. And we made the decision in the enlarged model, the cardinals and ordinals will remain the same as the previous one. No change. Okay? Okay. How do you do this? Well, let us see some practice. Okay? You see, whenever you have a complicated problem, try to simplify it. We thought of adding LF to many subsets, right? Array, forget about that nonsense. Just add one new subset of omega. How do you do that? Okay? Let us denote this set by A. For you, the whole thing looks non-rigorous. Of course it is non-rigorous. Okay? You don't think that Bhupen Hazarika's folk thing is non-classical. There is a classical thing in Bhupen Hazarika's, okay? But it is a folk tune. This is all folk. This is all non-rigorous. But however, things can be made precise. Okay? And unfortunately, when you try to make things precisely, then you will lose all this feeling. You should not lose it. Okay? So you should have a feeling first. Okay. We have a model M. We should be able to talk about the subset A. We want to add a new subset. Staying in M, because M is our model. We want to talk about our new model sitting inside M, because M is my model. Whatever I want to say, I should say in M. At the same time, this should be new to M. Okay? I want you to understand this is a deep, subtle philosophy. Okay? That is why Cohen's forcing in thinking. Okay? And you should understand the deep, subtle philosophy and the thought process. Mathematics comes automatically if you know what is to be done. Okay. So M is a model. You want to add a subset. You want to talk about the subset staying in M, but this subset should be new to M. It should not be in M. How do you do this? Well, the only way is to somehow think of a method whereby you can answer questions like, does 1 belong to A? Does 2 belong to A? Each question you should be able to answer. Okay? Then you can talk about the set A. But this, if you can answer all the questions, then your set is already in A. So, but you cannot answer for all n at one stroke. Okay? This is a logical point. Okay? Don't miss this. If you miss this, you will believe if you can answer 1 belongs to A, 2 belongs to A, 3 belongs to A, etc., you have answered all the questions. But please remember, this innocent, okay? Each given, okay? Each given, okay? You cannot ask infinitely many questions, only finitely many in any model, right? Therefore, each given question I can answer, but I cannot answer all the questions, okay? If I cannot answer all the questions, the set is not in M, it is new. If I can answer each question, I can talk about the set, okay? Whatever I want to talk about. Okay, so this is the whole idea. This is the crux of the matter. Okay. So, need a creator or an oracle to provide yes-no answers for each of these questions. Okay. Obviously, if you know answer to any such single question, you also know answer to any finitely many such questions. Okay, that's no problem. Only infinitely many is out of bounds. Therefore, well, friends, all this looks like a meaningless discourse, but every meaningless discourse precedes any meaningful work. Let us start the work. Let us start with a poset, the collection of all functions whose domain is a finite subset of omega and range is 1, 0. This is a poset in a natural way. Okay, domain of the function is a finite subset of omega. And what is the poset? F is less than or equal to G. If the domain of G is larger than domain of F, both are finite domains. And for every point in the domain of F, G gives the same value as F does, or G is an extension. Okay. Where is this P? This must be in your M. Okay. You may suddenly get it out, oh my God, where is this set P? Don't worry. There are enough theorems in set theory to tell you that this set P must be in your M. Omega must be in your M. Finite subsets of omega must be in your M. All such functions must be in your M. These are all theorems. Okay. Pick a consistent full set from P which does not represent any set in M. What do I mean by a consistent subset of P? A consistent subset of P means a subset of P so that if there are two functions f and g, either f less than or equal to g or g less than or equal to f. Okay? Full set means for every n, there is a function which tells you fn is either 1 or 0. Then that represents a set, isn't it? Every 0, 1 valued functions on omega defines a subset of omega. All points where the value of the function is 1, right? So any such consistent full set defines a subset of omega. But that subset should not be in omega. Now, before I proceed, let me just give you an idea. Suppose f is in P. If f of 5 is equal to 1, that means f forces 5 is in our set. If f of 5 is 0, then f forces 5 is not in our set. So every function here is forcing something on you. And a set f which satisfies this condition is called a generic set. Okay? It is called a generic set. So the question is, we can build a model which has this generic set in it. Okay? If you can build a model which has this set in it, that will be a new model and so on. Now, of course, that involves construction, and not only that, we need to build a model of ZFC, not simply a model for a new subset of omega. Therefore, the forcing concept comes. Not only 5 belongs to A is forced by this function. 5 does not belong to A is forced by this function. You have to define the forcing concept for every formula of set theory. That is what you need to do. Carefully understand. Now, how do you achieve this? You have to take a consistent subset, but that should not be in M. Aha! The set model is countable. In particular, P is countable will be useful here. Okay? Because P is countable, because our model is countable, there are only countably many subsets of omega in the model. Therefore, you can carefully select a consistent full set satisfying this condition. Okay. Before I proceed, let me tell you one thing. Just now I made a statement. Unfortunately, just like politicians take statements out of context, in mathematics also we take statements out of context. Don't do that. I said M has only countably many reals. Don't take it out of context. Okay, M is a model of ZF. In M, there is a real number system. In M, there is, okay, a real number system, and you can show real numbers are uncountable. No disaster. What does that mean? In M, there is no function which maps omega onto that real number system in M. Therefore, according to M, there is no such function from omega to R. Therefore, R is not countable in M. Okay? But I am building external models. I am looking at M and there are countably many reals. Therefore, I can get such a tree. Okay, that is the subtle point. You have to be careful. Okay, there is an interplay between what I am doing internally, what I am doing externally. Okay, getting hold of this set is externally. Okay, and therefore, now would ordinals and cardinals remain same? Yes, that is where countable chain condition of P comes into play. This partially ordered set satisfies something called countable chain condition. Okay. Therefore, I will not go into the details. Okay. And that makes ordinals and cardinals remain same, no change. Now, staying in M, you can talk about the enlarged model. In other words, there is a representative in M. So if you think of capital N as the enlarged model, namely the model M enlarged by adding the set A, and now please remember, you can't enlarge just A. You have to get a complete model of ZFC, enlarging M. In that new model, this set A should be there. What is the set A? A is the set determined by this generic thing. Okay? Namely, the set of all points X such that Fx is 1. Okay? For some F in P. Okay? All right. So, you will be, there is a representative for everything in the new model N, there is a representative X in the in our original model M. So whenever I want to talk about the new model, I keep on talking about that point X in this model. All my statements are made in the model M. I will not go out. Staying in my model M, I talk about the new model. Okay? And I show staying in my M in the new model. Okay? There is a subset of omega which is not in correspondence with this or that. Everything staying in my model. The construction is done externally. Okay? So there is a subtle point. You have to carefully understand that. All the statements are proved staying in my model. I am not getting out of my M to talk about things in the new model. This new set A in M, in the new model, okay, the new set we have attached, that is not in my M. But still, there is a way to associate something in my model M so that by looking at that something, I can talk about A. Okay, that is the beauty. Okay, this is a big edifice. I will not go any further, but this is the main idea. Okay, so the main idea is to create a creator who will produce a new set. New set means that should not be in M. But you should be able to talk about new set sitting in M. That means for every given integer n, you should be able to answer n belongs to A, n doesn't belong to A. Okay. This is what is achieved. Okay. So, now, how do you add Aleph to many sets? I will not go in detail. Okay. If you want to add Aleph to many sets, then what you do is the following. You can look at a function from omega cross Aleph to in M with values in 0, 1. Okay. I have added a function on omega earlier. You see, once you understand the trivial idea of adding one set, there is nothing to prevent you. Okay. You should get a foothold. Then you can lie down. You add a function on this to this. That function will give you Aleph to many reals. Why? If you fix this second coordinates, it is a subset of omega. If you fix a point, okay, it varies over here. Now, I leave it for you. You have to achieve it in such a fashion that you have got distinct subsets. Okay. Every point here determines a subset of omega. Okay. Fix the second coordinate as a function of the first coordinate. It gives you a first subset of omega. You must make sure that those are distinct subsets. And as I said, I wrote Aleph 2 super M. Okay. When you go to the new model, Aleph 2 super N is still Aleph 2 super M. There is no change. It is still Aleph 2. There are Aleph 2 many subsets. Okay. So I leave it here. How do you show ZF plus negation AC is consistent? You need to work a little hard. Okay. Again, go back to the idea. Russell, if I give you a pairs of shoes, you can give an algorithm to select one from each, say left pair, left shoe. If I give you a collection of new socks, you cannot give an algorithm. Why? Because there is a symmetry. Okay? The two socks, when they are new, there is nothing like right and left. Okay? So the collection of socks are invariant under a symmetry. Okay? What is the symmetry? Transposition. Okay? Look, take each sock. Well, I don't know what you should call socks or whatever. Okay? Take one pair of socks. Okay? Alpha, beta. Exchange alpha with beta, beta with alpha. That pair remains the same pair. Okay? On the other hand, right and left, if it is written, it won't remain the same. That is a beautiful idea. That is why you are not able to do an algorithm. So Cohen makes that idea work. Okay? So getting an idea, please, these are the points you should take home. Okay? Getting an idea, making the idea work, execute. Check, there is nothing wrong. Okay. Starting with a countable transitive standard model, you enlarge by adding a sequence of new reals. Okay, you have just now seen how to add one real and a collection of reals, lots of reals. So add a sequence of reals. They should look alike. Okay. Oh my God. How do I add reals which look alike? Okay. Well, how did you add a real? By looking at the partially ordered set and taking a consistent full set from P. Okay. So take a group acting on the collection of functions. Okay. And look at invariant things. That is how you get. Okay. You get a model in which there are a sequence of new real numbers which look alike. Okay. Of course, at this moment, it doesn't make any sense to you and to me. What is meant by saying that they look alike? Okay. That means they are invariant under certain invisible group action. Okay. That it is not hard for you to see what the hell is the group action too. Okay. After all, permutations act on omega, right? So you can look at that. Okay. You look at finite permutations and so on. Okay. Only finite set you can talk about. There are reasons. So if there is a finite permutation of omega means any one-to-one onto map of omega to itself, which changes only finitely many points of omega. That is a set. That is a group. That is in your model. You can show theorem. Okay. That group acts on the partially ordered set. Obviously, you have to look at generic sets which are invariant under that. Okay. Now, you get a new model and a sequence of reals which look alike. And in that new model, you have to take a sub-model. That new model is not the model to show negation AC. Okay. You have to take a sub-model which are definable. Okay. Why do you have to take definable? Because the idea in this word, they look alike, is that they cannot be defined. Okay. You can't distinguish. That is the whole idea. I will not go in detail into that. I leave it at that. So that is how he shows. That is a more complicated model. So you have to take an external model and then you have to take an inner model of the external model. Okay. So you will see the beauty, the edifice, the palace. Okay. Built by Cohen. Okay. Now you see, you can take your own partially ordered set and so on. So million things have been done ever since. Unfortunately, Gödel's axiom is a dead end. By dead end, I don't mean you end up with a wall. You end up in a beautiful garden. You have only to roam around in that garden. But Cohen's is a highway. Okay? All right. Now, that is Cohen's method. Now, I will just take 5 minutes and give you time later to ask questions. Soloway, Robert Soloway, Dana Scott, and Openka, they have realized that, wow, what Cohen has done is, instead of taking the truth values 0 and 1, you take truth values. Oh, how come I have omitted? Oh, I see. Anyway, okay, sorry, that thing is gone. Okay. Instead of taking truth values 0 and 1, you take truth values for formulae in a Boolean algebra. Okay. I think I will not define a Boolean algebra. You can think of it as a field of sets where you can talk about union, complement, and so on. Okay, as Kuber must have told you. And usually you assign truth values for basic formulae, then you define truth values for more general formulae. For example, for phi or psi, you define truth value 1 if one of them is 1. If both are 0, 0. Exactly the same thing. Truth value of this will be truth value of this, union truth value of this. And the truth value of negation phi is truth value of this one. There is this x phi x. Okay, how do you do that? You have to start with a complete Boolean algebra. What is complete Boolean algebra? Complete Boolean algebra means in a Boolean algebra, given any two things, there is a max and min. Complete Boolean algebra means there is a sup in for any given family of sets, any given family of elements in the Boolean algebra. Don't worry, I will give you an example of such a Boolean algebra. Okay, there exists x phi x. How do you associate truth value? For every a in your structure, look at the truth value of phi a, that is an element of your Boolean algebra. Take the there exists x. Union, maximum of all the truth values of phi a. That is the truth value of this. Okay, I leave it for your imagination. If you know Boolean algebra, complete Boolean algebra, it is not difficult. So they realize that this is same as Boolean truth values. What is a good Boolean algebra? Now, the next 3 minutes, you have to bear with me. I will talk about a probability space, that is a measure space, a set and a sigma field of sets, and P is a measure on that. You can think of unit interval, you can think of Borel set, you can think of Lebesgue measure, or you can think of any product of unit intervals, product measures. How do you get a Boolean algebra out of it? You look at all sets here, modulo null sets. N is the collection of all null sets. You say the two sets here are equivalent if measure of the symmetric difference is 0. Okay, that is an equivalence relation for sets, and the collection of equivalence classes is a Boolean algebra. Okay, that is a complete Boolean algebra that satisfies countable chain condition, by the way. Okay, then what they said is the following. Look at the collection of all random variables on this probability space. That forms a model for real number system. Okay, please listen carefully. The collection of all random variables, real value. Okay, anyway, we are talking about real numbers. Okay, so we have ZFC, we have real numbers. So the collection of all real valued functions on this is a complete Archimedean ordered field. That is what they showed. Okay, you will be surprised. How do you associate truth values? For example, if you take two random variables or two measurable functions, what is the truth value of this formula? Look at the set of all points where fx equal to gx. That is the truth value of this. This is a set. Okay, and therefore this is an element in your Boolean algebra.
What is capital X here?
What is the truth value of this? Look at
No,
the
what
set
is capital
point where fx is less than gx. That is the set.
Professor, what is capital X here?
Oh, wait. So I have a probability space, capital
okay,
X,
okay.
and a sigma field and a probability.
Right.
Okay. Yeah. Now, H is equal to F plus G. What is the truth value of that? Look at the set of all points X where Hx is equal to Fx plus Gx. That's the truth value. Please remember, truth value is different from empty set and whole space. Okay, it could be in between. Okay. Now, you will wonder, oh my God, then how can it be a field at all? Given F not equal to 0, is there a element H such that Fh equal to 1? Of course, there's an element H. Why? Take any random variable F and look at the following H. When F equal to 0, define H anything you like. When F is not 0, define Hx as 1 by Fx. I want you to carefully understand, okay? If X is a point where Fx is 0, define Hx to be anything you like. 31. When Fx is not 0, define Hx as 1 by Fx. Then the sentence is correct. Why? How do you calculate the truth value of sentence? You see, logic comes into play. Truth value of this sentence means, what is the sentence? Negation of this or this. Negation of this means what? F equal to 0. And this. So what is the truth value of that? Truth value of that is the set F equal to 0 union truth value of this. I leave it for you, the trivial verification. That is the whole space. Okay. And there is exactly one H also. Okay. So beautifully, all axioms for complete Archimedean ordered field hold. This is a model for real number system. Now you can see, if you take a huge probability space, there are huge number of real numbers. Therefore, that will be a model where CH is false. Okay, I gave you a glimpse, but this is glimpse into thinking of real numbers free from continuum hypothesis. But this is not all. You have to build a model for ZFC. In that model, real number system, you have to show. Okay, that can be done. Now the question arises, okay, I don't like your Boolean valued models. I like only 0 and truth values. I hate truth value being something between 0 and 1. Please don't worry. Mathematics tries to satisfy everyone. Okay, no dissatisfaction. You know what is a homomorphism? From this Boolean algebra, you can take a homomorphism to the 2-point Boolean algebra. Okay, I think Amit must have talked about it. So if you take a homomorphism to that, you will get a 2-value model too. That's not a problem. I leave it here. So what I do is the following. There are excellent books, Schoenfeld, Thomas Jett, Kenneth Funen, and so on. There is a nice paper, Paul Cohen, The Discovery of Forcing, Rocky Mountain Journal, and Dana Scott, A Proof of the Independence of Continuum Hypothesis. And these are there in the notes. Okay, so I leave it here, and I will now answer all your questions. Please don't hesitate. Okay.
Hello, sir.
Yeah, ask.
There is a question from YouTube.
Ah.
Can I ask it, sir? The question is as follows. How do we know that generic sets exist?
How do we know that?
Generic sets exist.
Oh, sure. That is the execution part, you see. So I have told you the idea. Okay. Now, when you want to execute an idea, you have to realize what is before you, right? So the idea is to make, let us say, potato curry. To execute that, you should say, do we have potato? Do we have other things? And so on. Okay. So idea is different from execution. Now, how do you execute the idea? Now you go back and ask what do you have before you? You have a countable model. If the model is countable, then the number of elements in that model is countable. Therefore, the real numbers there are countable. Okay? And as a consequence, okay, you can take each real number in your model. Let us say alpha 1 is the real number. Suppose n1 is in your alpha 1. I will make sure that 1 is not in my set by putting a function such that f of 1 is 0. Okay. I take your second real number, alpha 2. Suppose 2 is not in your real, is not that subset alpha 2. Okay. I am thinking of real numbers as subsets of omega. Okay. So 2 is not in that subset. I will make sure that 2 is in my subset. So I will put the function, okay, g, whose value at 2 is 1. Like that, I will put in my collection G, remember, I have to select a full consistent subset of P. I will select a full consistent subset of P so that one element there contradicts the fact that this final set that is going to be defined, okay, this is unending, will not agree with the set you showed me. Okay, that is how you get a generic set.
Professor Rao, what is the reference for the last part which you said about random variables in the probability?
That is Dana-Scott, Mathematical Systems Theory.
Mathematical Systems Theory by Scott. Okay.
Dana-Scott. Oh, it's there in the notes, but I can tell you, yeah. You see? In fact, Boolean valued models have brought to fore measure algebras and so on very heavily. Okay? Yeah. And you see, in fact, Robert Salovey and Dana-Scott will joke. We were stuck with true-false valued model. If we have thought just Boolean valued models, we would have got the Fields Medal instead of Cohen. Okay. Unfortunately, we did not. You see. So once Cohen discovered his model, people realized, and you will ask, what is the relation between the partially ordered set and the Boolean algebra? Well, topology comes into picture here. On a partially ordered set, you can define a topology. That topology gives rise to some regular open sets. The collection of regular open sets is a Boolean algebra. And what Cohen does with his partially ordered set, you do with this regular open Boolean algebra on the same partially ordered set. You get exactly the same model. Okay.
I missed the joke because of internet connection. Can you repeat it, please?
Yeah. No. Salovey and Dana-Scott say that our mindset is to think of only two valued models, 0, 1. Okay? If only we thought better to look at truth values between 0 and 1, taking values in a Boolean algebra, then probably we would have got the Fields Medal instead of Cohen. Okay? Yeah. So you can ask any questions now, doesn't matter. You see? So what I wanted to say is, you say you can deify anybody, you can say Rama is God, but as long as you think about that, you do nothing. Okay? But only when you think Rama is a human being, he was a human being, he did this. Why can't I do that? Okay? How did he do it? Only when you analyze, then you see the greatness. Okay? You can appreciate great people, but the awe you have, you continue to have it, but at the same time, ask yourself, how could I have done it? What is the idea behind it? Okay.
Sir?
Yeah.
So my query is from your last lecture, yesterday's lecture.
Yeah.
So that the proof of that AC implies well ordering principle or AC implies Zone's lemma.
Correct.
So
yeah.
The proof how ordinal or cardinal come to in the picture for that.
You see, okay, good. Whenever there are 4 junctions, okay, it is always good to see how you can go from each junction to each other junction, okay? But so here also, you can directly see, without going to the well-ordered principle, you can directly show axiom of choice implies John's lemma, okay? But since I am lazy, I have proved that axiom of choice implies well-ordering principle, okay? I have used well-ordering principle to show John's lemma. That is why I did that. But let me tell you, there are proofs without going through this junction, well-ordering principle. That is number 1. Number 2, and how did I show that? I used recursive definition to get a maximal chain. Okay? I started with any element. If there is nothing bigger, finish. This is maximal, over. If there is something bigger, that will be f of 1. If there is nothing bigger, over. If there is something bigger, that will be f of 2. So I defined it. I do not know how far I will go. Okay? I may go all integers, but still there may be something beyond.
Yeah.
Therefore, I have to use ordinals. I may go beyond. Okay? And then there comes a stage where I stop because I have a set. I can't go on forever. Therefore, after I stop, I look at this is the maximal chain. Look at the upper bound of this maximal chain. That has to be an upper bound. Okay?
Sir, that the reason we cannot go beyond the ordinal because this is a set. Why? I do not understand this.
Okay? Because I have a partially ordered set. Okay? I am defining a function. Suppose my partially ordered set has cardinality, let us say aleph. Okay? Agreed? Okay. Let us take a cardinal bigger than aleph. Okay? Now, I will define only up to that. That is good enough. Okay? So you try to do this construction, then you will realize. You see, my recursion is generally, the definition by recursion is stated in two different forms. Number one, it is defined on the collection of all ordinals. But in my notes, I have not defined on all ordinals. I have taken an ordinal alpha. I have given the theorem definition of a function on alpha by recursion. Therefore, here you will ask me, if you want to apply your definition, which alpha are you taking? Okay? So that is why I said I have a partially ordered set and take an ordinal alpha whose cardinality is bigger than the cardinality of this partially ordered set. You will not go beyond that. That's all. Okay? So once you start doing it, you will realize that's it.
Okay, sir.
Yeah.
Hello, sir.
Yeah.
So, this is not a technical question. I just wanted to know your personal opinion about the implications of all these, like set theory and meta mathematics and all that you said on reality, like the nature of reality.
Nature of reality.
Yeah, because this is like, I mean, I feel like there is no single truth when you study all this. It's like,
Wait a minute. But the moment you said reality, you are assuming that there is a reality, right?
yeah. So,
But
yeah.
is there a reality? That's the main question. Is there a reality? Okay.
Yes, sir.
Yeah. So that's it. So basically, what you are going to do is what can be deduced from certain statements. That's it. That's what you are analyzing.
So it's like humans can never know if, I mean, what is actually out there.
Yeah. Sure. You never know. You see, what do you mean? What is out there? We don't even know what is in there.
Yeah.
We know what we are feeling. Nothing. We know nothing. Okay. So don't worry. So it is always great to know that the axioms of ZFC would not prove continuum hypothesis. The axioms of ZFC would not prove negation symmetry. Okay? That's it. But what you do with that is a different thing. Okay?
Sir?
Yeah.
Sir, yesterday we have defined this two as singleton, two as set phi and singleton phi.
Yeah.
So that is two consist of two elements.
Yeah.
So here, do we use this idea like here defining this two, we have used the idea of two which we already like previously known.
But who asked you to say that this is two sets? I gave the name two to do that. That's all. You see, the thing is, which comes before what? Okay? Seed or plant. So I said 5. This set consisting of 5. These two. I named it as 2. You said, okay, how are you using 2? Don't use 2. I named this as 2. Okay?
Okay, sir.
The picture 2 came after this. But you say, just as I said, remember again in the beginning, you say, we should greatly appreciate our parents and teachers in the elementary school. Okay?
Yeah.
They never forced us to understand what exactly is frequency of light wave and red color, green color, and so on. They made us familiar with all these things. Okay? Only when we grew up, we realized what is the difference between the colors. Right? In the same way, they familiarize us with these pictures 1, 2, 3, 4, 5, etc. so on, which we call numbers. Okay? But what are they? Okay? We never asked, we never understood. Okay? We all pretend we understand them. That's it. But what is it? If somebody asks you, can you show one? No, there is no one anywhere in the world. You can't show. You can show one pen, one chair, one apple, but no one anywhere. You see?
Okay.
So that's all. So that too, you are absolutely right in asking your question. Don't worry. Ask all questions. Okay?
Yes.
Yeah.
Hello, sir.
Yeah.
There is one more question from YouTube Live from Shamik Paul.
Yeah.
The question is as follows. How can we, sir, can you please describe one more application of forcing? That's his question.
Oh, one more application of, first of all, let me tell you, forcing has millions of applications. Okay? You can talk about, for example, long ago, great Polish mathematician posed a problem. Sorry, not Polish, Russian, I think. Yeah. Posed a problem. Okay? Real life has the following property. Okay? It is a linearly ordered set. It has no gaps. Okay? Every bounded set has a sup and min. It has no sup, no min, no minimum. And it satisfies countable chain condition. Would all these things, okay, characterize the real life? Okay? That leads to a topic called Suslin trees, Suslin lines. So, is there such a thing which is different from real life but satisfies these properties? And to answer that question, again, forcing is the idea. Okay? And there is a huge story behind this. Forcing is like a palace. Okay? There are several stories in the palace. You start with a model, forcing, you can construct a bigger model. Now you sit in that model, force, you construct higher model. Okay, go one story up, one story up. You can ask, can I do this at one stroke? Lots of questions, okay? So forcing has opened up, as I said, it is a highway. It has opened up, okay? There are several things that will do this. For example, okay, I don't know why I went to that Suslin tree. I could have said trivial example.
No, but Bibi, just 1 second, let me interrupt you. I'm sorry. Countable chain, you didn't mention separability. That Suslin line is, those properties,
right.
Which is separable, which satisfies countable chain condition but is not separable.
Not separable. Yeah, that's why.
That's not what you said.
No. I said, does it characterize real life? That's all. Okay. I said, does it characterize real life? Okay. Yeah. Okay. So, is it okay?
Anyway, it's okay for me. I know the story.
So, the second thing is the following. I could have said a simpler thing rather than Suslin trees. Unfortunately, I said that. Forget about it. Look at the real line. Is every subset of the real line Lebesgue measurable? Okay. With axiom of choice, you can say not necessary. Okay. What about this statement? Again, forcing method. There are many forcing methods. Okay. Discussing several things. That's a highway.
Hello?
Yeah.
So one more question is for that continuum hypothesis that you say you give the idea how to prove that continuum hypothesis is true in Gödel's model. So in that case, you start with that empty set and you construct L alpha with countable ordinal, and then you say that take the union. So
Right. What did I say? Union over what? Alpha belonging to?
Alpha belongs to all countable
No.
ordinal.
Alpha belonging to all ordinals. Okay. That is a model.
That is a model.
ZFs. Okay.
Then
that is why it is a class. If you stop at some stage, it is a set. So keep on defining L alpha. Union over all alpha on ordinals L alpha is a model of ZFC. In this model, okay, real numbers are only Aleph1 many. Why? Because every real number is constructed before L Aleph1 and L Aleph1 has cardinality Aleph1. Okay?
Yeah.
Every real number appears in L Aleph1 and the set L Aleph1 has cardinality Aleph1. Therefore, real numbers are Aleph1. That is what I said. Is it okay? But don't worry, you can ask.
So I do not understand because
What is it you don't understand?
Sir, it is. I understand that L alpha, the cardinality of L Aleph1 is countable. This set is countable.
Sorry. The cardinality of L Aleph1 is Aleph1.
If Aleph1, then why it is equal to R?
I never said it is equal to R. Listen very carefully. This set L Aleph1 has cardinality Aleph1. And the second statement, every real number is in this set. Therefore, what do you think?
Oh, so
the cardinality of the real number system
is less
it is
than
not countable. We know it is not countable. Therefore, it must be Aleph1, right?
Yeah.
Yeah. Correct.
Sir, how had you shown that every real number appears up till LF1? I didn't get it.
You see, you have to use Löwenheim's Coulomb theorem and so on. Okay? If a real number appears in a structure here, it appears, okay, in a countable submodel, then there is, I don't remember the proof exactly right now. Okay? I do not know whether it involves Mastovsky's transitive collapse, whatever.
It will.
It will, right?
It will.
It will involve Mastovsky's transitive collapse. You have to do all that thing. Okay? You have to take a countable substructure. You have to take a Mastovsky collapse. Okay? Etc. That is how you should.
Hello, sir.
Yeah.
So also, like during a previous class, you said everything can be constructed out of emptiness, right? Like, yeah. So, what philosophical implications do you think? I mean, what did you what philosophical implications did you have in mind?
You see, mathematically that is right. That's all. Okay, but philosophically we can't interpret. You see, because you see, somebody said in mathematics, okay, you are free to make your own definitions, right?
Yes, sir.
So somebody said the following, I forgot the name, you are somebody, okay? You can name a symmetric real matrix as an elephant. You can say spectral representation, trunk, okay? Every symmetric matrix has a spectral representation in linear algebra, right? So you can say I have proved every elephant has a trunk because I define elephant as a symmetric matrix and the trunk as spectral representation. Every elephant has a trunk. However, don't pretend that this has anything to do with real elephants and real trunks. Okay? So there you have to be careful. Okay? So we defined empty set, we defined axioms, we defined that all these things built out of empty set satisfies all the axioms of ZFC. That is fine. But if you want to think of it, everything came out of nothing, you can say. You see?
Yes, sir. Yes, sir.
These are all a little heavy statements. I don't know anything. Okay?
Yes, sir.
Yeah. Good.
So I think it's basically what somebody believes, like it's personal. Yeah.
Right. Right.
Probably sad you are not, you don't subscribe to formalist idea from from this that I see from the chat box, that you don't subscribe to a formalist idea. And
No,
somebody,
sir. No, sir.
somebody said that mathematics, I mean, here is a, you know, we mathematicians are formalists. No.
Yeah, sir.
We
I know.
start with axiom, we prove the consequences, and that's it.
Yeah, sir. But I'm saying, basically, in mathematics, you don't want to associate with any intuitive idea, like any visual picture or anything. Yeah, but I'm saying if you associate with real world, or if you do something like that, it gives more beauty. Like you can have your own philosophical interpretations of.
No, but Chad, let me ask you one question.
Yes, sir. Yes, sir.
Today I talked about this, that every non-empty set of integers, natural numbers, has a least natural number.
Yes, sir.
Was it obvious? Is it obvious?
Sir, actually, you're deriving that from the axioms.
You see, so when Samik asked me what is the difference between N and PA, I told him that, axioms of N are kind of trivial axioms, you see it. But there is something there in the method of induction. Okay? Actually,
Yes,
you assumed it. Okay? That was
Yes,
one
sir.
of the axioms that you started with. You didn't prove it.
Yes, sir.
But when we built, when B.B. Rao gave you a model of natural numbers as
Yes, sir.
that thing, was it clear?
Yeah, you can actually prove that, right, in that model.
Really?
For that,
Why? How?
using.
For proving anything, you need an axiom.
Yes, sir.
So axiomatically, how can you prove it? So now the interpretation of, I gave the interpretation, and maybe B.B. Rao, I have not heard fully B.B. Rao, that less than is interpreted as belongs to.
Yes, sir.
And then there is a foundation axiom which is not seen by mathematicians.
Yes, sir.
That will tell you that there is no decreasing sequence, strictly decreasing infinite sequence with respect to this relation. Okay?
Yes, sir.
And if you don't assume, sorry, what happened? Over. Oh, time is gone. Can you hear?
Hello?
Yes.
Okay.
Yes, sir.
So if you don't assume foundation axiom, in set theory you cannot prove that
So I
omega
didn't hear the last part. You can.
What I am saying is that you have not seen what are natural numbers. And you said your parents did a very beautiful job. They gave you a picture.
Yes, sir.
But when you started deciphering that what are these, what are these, what are that, at that time, now B.B. Rao has given you a picture.
Yes, sir.
That he calls empty set 0. He calls, he defines 1, 2, 3, ... And then, then now the question arises that this B.B. Rao's model, does it satisfy piano axiom, induction axiom? Okay?
Yes, sir.
So this regularity axiom or foundation axiom, if it is not put there, it will not satisfy. I mean, it is not, you can't prove it.
Yes, sir.
Okay?
Yes,
The
sir.
whole thing, even probably everything that I will say about natural number will look like a thing in the real world to you.
Yes, sir. Yeah.
But you don't know what are natural numbers.
Yes, sir.
So there is an illusion there.
Yes, sir.
There is an illusion there.
Yes, sir.
So that axiom has been put. Now one can ask, why should I put that axiom? It is not obvious to me. Well, that's it. We don't care.
But we decide the
And
axioms based on what.
like he gave a sort of possible universe of sets, there also this axiom is very much needed. Only thing is that our satisfaction is the following, that if we assume all these axioms, the main job of set theory, main job of the set theory is to lay the foundation of mathematics.
Yes, sir.
So once we start with these axioms, we can define mathematical objects. Okay?
Yes, sir.
Now it is up to you. Like we have a friend here, Ranjan Babu. He will say that no, I will not accept propositional axiom as an axiom. That is also a formalist view.
Yes, sir.
You should realize that mathematics is a formal science.
Yes, sir.
And what you are talking of real world,
Yes, sir.
is a little bit of an illusion.
Yes, yes.
Okay.
Yeah. Thank you, sir.
Yeah.
Yeah, somehow my thing went off. Yeah.
So I guess we are done with the questions then. Can we conclude the session?
Yeah, but before concluding, maybe you should announce when we should meet in the afternoon. 2:15 is the usual time, right?
Yes, sir.
Yes, 2:15.
So shall we make it 2:30?
You want to make it 2:30?
No, I'll be ready by 2:15. Doesn't matter. But many may not be able to come. I'll be ready.
Yeah, I mean, let us.
Okay.
Yeah, we can postpone it by 10 minutes, 15
But
minutes.
anyway, we can start
We can
at
start at
2:30.
2:30.
Yeah, the meeting can start at 2:15. Okay.
I mean, the participants are still here, so maybe they want to have lunch properly.
That is why I was
Start
wondering.
at 2:30, and the schedule that is available for student presentations on the website, that will all be postponed by 15 minutes.
Okay, yeah.
And here I would like to take the opportunity to thank all the speakers from the program committee. Thanks for accepting the invitation, Professor Rao and Professor Sarbadikari, if she is still around.
Yeah, hey, madam, come here.
I mean, SMS is also one of the program committee.
Yeah, so we don't thank ourselves.
Yeah, exactly. So therefore, I made the job easier for you to thank your wife.
No. She will not be satisfied with that.
What is that? Oh, you are supposed to do the thanks.
Thank
everybody else. Thank everybody else. Thank the Bhopal people.
Yeah.
Can I
Yes.
Can I, as a participant, thank Hoymont Didi?
Yes.
As a participant, I am now thanking Hoymont Didi and also Professor B.V. Rao and Kuber and SMS are program committee members, so they are in any case supposed to provide us services. So
no, you thank us twice. One as a speaker, one as a program committee, and then
right.
And you must not forget the local organization.
Oh yes, of course, yes. I thank everybody here. Right. Thank you.
Hope we shall meet. Okay.
Oh sure, of course.
Now Sujata has to say something.
Yeah, I'm just saying that we do have the student presentations.
Yes.
Please do come.
Yes, definitely.
Well,
everybody should come to cheer up the presenters.
But I will not be here.
Sessions, but I was aware that these two people won't be here, so that's why I said thanks.
Okay, but I will try to open my smartphone.
Okay.
Wherever I am.
Okay, no problem.
Okay, I'm leaving. Go and
So can I end the meeting then?
Yes, we'll meet again at 2:30.
Sure, sir.